Non l'abbiamo portato?
Ecco qua, si
Ah, perfetto, bene, bene.
Aspetta.
Così se dico scemenze mi sentono tutti. Meglio del solito, tra l'altro. E Polas. Ho fatto l'errore madornale di prendere uno Strohwaffel prima di venire qui. La secchezza delle fauci. Buoni, probabilmente è la cosa migliore che è uscita dall'Olanda. Però se siamo live non posso ovviamente un commento non proprio da fare.
Funk time.
Yes. Pa, pa, ok. Rompiamo il ghiaccio oggi. Se vado in bagno si sente tutto. Se vado in bagno devi staccare il microfono.
Basta che lo chiudo, se vuoi
Ah,
lo chiudo e andare prima dopo.
il piovra, ma no dai, ci siamo, tanto...
No, meglio andare. Aspetta, meglio
Sì.
andare. No.
Dai, non corriamo rischi. Direi.
Yes.
Can you hear me from? Yeah, well beyond this room. Exciting.
Veramente tu non arrivi fino a là sotto.
No, no, al massimo nei
Fino alla
pressi della sedia, ma
Perfetto.
Marco, sei pronto per il lightning talk? No. Devi rifarlo. Sì, che vuoi? Come fare test in produzione like a Gen Z. Pensaci. Vedete, questi sono i dati live di Flowy, ecco, se io faccio così... Sì. Capisci? Cioè, guarda.
Okay. Now we are ready to start. Welcome to the Tagliatelle room. So now Luca Baggi talks about FunkTime, a next generation ML forecasting library powered by Polaris. I remember you that there are a Q&A link in the scheduled detail of this talk. Thank you, Luca.
Thank you very much. So, hello everybody. It's a pleasure to be here yet another year. Twice the room, actually. Same snake, actually new snake, new t-shirt. So that's a new experience for me as well. So today, my name is Luca, as I was introduced. So thank you very much, Santino, for the wonderful introduction. And by day, I work as a ML engineer in Extreme, and by night, an open source maintainer. A burden I've taken upon myself since the past year or so. So anyone here contributing to an open source project? Yeah, bunch of people in the room. Okay, good. How's been with the life balance, health-work balance? Okay, not so ideal, right? But how many of you here are here for forecasting, especially? That's cool. And I kind of appreciate that not a lot of people are here, because the point that I would like to make today is twofold. There are also people that will learn a bit in the next 20, 25 minutes-ish about forecasting, but what I would like to showcase here is that I cannot use a pointer. Or more precisely, that this FunkTime library, which is experimental in a way, but could be somewhat sneakable into real production code, is built upon polars. And on its own is a bet, a living example of how polars, which I've talked about extensively last year, in case anyone was here on the last edition, can be used to build a next generation of tooling. Polars has wonderful characteristics, and this is mostly a demo of how we can use polars to envision a next generation of software, developing its capabilities and maybe allowing ourselves to experiment with the APIs. So my goal for today is to briefly introduce you to one of my domains, which is forecasting, and how it can be seen as a problem on a broader sense in terms of the whole machine learning with forecasting process on its own. And then see how FunkTime attempts to offer a somewhat opinionated bias solution that works for the 90% of the use cases. And here they will follow up with the two ingredients that make this possible, polars, of course, and then one of the latest trends in forecasting, which is global forecasting. And finally, I would like to endeavor myself in the really extremely dangerous field of live coding during conferences that are being live streamed. I'm not as expert as one of my colleagues, Cesare from Python Milano. He will be speaking tomorrow. He's an absolute god of the, actually, maybe not that, but somebody like really goes against any kind of, anything that's sacred about demos, and he'll do like 1, 2, 3 live demos at once. I will be in a much more controlled environment, but still we'll be seeing some live coding. And finally, I will do a couple of references and this type of stuff. But that's the juicy stuff. And I can't say forecasting is broken. Maybe now it's a bit less popular because we're talking a lot about generative AI, but it's one of those things that's evergreen and basically anybody needs to do. But forecasting is a tedious process. It's the work of an handicraft who needs to take care of every time series, look at the residuals, fit the models. We do have libraries that offer auto-tuning for some parameters, but nevertheless, it's a demanding process that doesn't scale. It doesn't scale because if you go to 13, 14, 15 time series, then it becomes a mess to handle all of the diagnostics. And if you need to scale this to a production or a Spotify-like level, then you need to have a cluster and run a distributed system or use a Spark with MLlib or God knows what to manage all of this complexity. And to achieve what, right? That's the whole point. We can sometimes struggle to beat naive baselines, which are a fundamental aspect of forecasting. And just to achieve what, right? To deploy a model in production after months of efforts, just to achieve a 2-3%, if it works, that's the premise, but you're not guaranteed to have it work. And maybe you need to retune it frequently, right? So as Mike Gilliland said, and he's on the board of the International Institute for Forecaster, and as well as a manager at SAP, he wrote a series of really interesting blog posts about where forecasting is heading, and it was a while ago. But this is actually the real point that he makes, and I think it's really interesting and tangible, and it has a really good point to make. We spend far too much time and resources about forecasting as a whole, And sometimes it's not really unlikely that we fail to achieve this goal. And so what he wants to suggest is that forecasting needs to become more efficient at a fundamental level in terms of a process rather than fit in estimator in a fast way. Okay? The way we can obtain gains from forecasting is not just about how we make algorithms that are faster or more precise, but how to make forecasting as a whole faster. And this is what Funtime wants to achieve, to make forecasting work for the reasonable scale, for the 90% of the people. For people that have a small business, for people that need to deliver production, they're not Spotify. For example, Spotify, Amazon, or whatever any other company that might have like a real advantage from working intensively on a whatever transformer-based model or whatever. And we do this and enabling the combination of the two ingredients I was talking to you about before, which are polars and global forecasting. We enable a swift and fast iterative process that allows you to forecast 1,000 of time series at once on your machine. I'm a bit biased, I have a 36 gigabyte Mac, but I think it's doable nevertheless, and it's doable, okay, without distributed systems. We also offer feature engineering and diagnostic state-of-the-art APIs to extract feature all at once from 1,000 time series at once and diagnose your whole forecaster on all of those time series at the same time. And this hopefully enables you to translate from experimentation to production. Because Polars is so slim and Funtime tries to be, that you can deploy it maybe on a Lambda, hopefully. And these are the two ingredients we do. So, how many of you know Polars here? Seems I've done my job, fair enough. Okay, it's a wonderful library. If you haven't tried, do give it a shot. You come for the syntax, you go there for the speed, and you stay for the syntax. It's an amazing library. It has an extending potential. I highly encourage you to try it out. But basically, it's pandas on steroids, for real. It's a multi-threaded vectorized query engine that has on top of it, a data frame library. So it's not SQL. You interact with it as a pandas object or a data frame object in Python. And it's extremely fast because it uses all core of your machine efficiently, unlike pandas, and it uses 50 plus years of research in relational databases to be extremely intelligent about the data are read and aggregated to perform an aggregation. And it is in process, a bit like SQLite, so you don't have to have like a server client infrastructure. And what can be so fast is that it enables like recent developments in the data ecosystem. For example, the Apache Arrow specification to represent data in memory. It employs Rayon, which is an extending Rust library. Oh, did I mention that Polar's code is written in Rust? I forgot about that. It's blazingly fast. And it implements work stealing, which is an incredibly smart, efficient way that anybody can understand about how it processes the work all at once. I won't delve into the details, but Richie Ving, the creator, made a couple of really interesting talks and keynotes about how this works, and it's so accessible and it's so elegant that you really appreciate it. But the whole bread and butter about this is that if you do this in pandas, you will incur in some overhead, because pandas will read whole data into memory, sort the whole data set, and then return the top 5 heads. So basically, it sorted the whole row for you, the whole column for you, and then it just took the first 5 values. Polars is clever. When he sees this, he knows how to optimize this, and it just fetches sorts the top 5, and there you are. So you didn't have to go through sorting the whole row, maybe being 1 million of results. Polars just does the top 5, which is a much more efficient algorithm, because only once it finds the first 5, then it's done. And then here comes the second ingredient, which is global forecasting, which is a really fancy way to say we just fit one estimator on all of the data, on the time series we have in our panel dataset or multivariate dataset. And this is a trend that's come up in a bunch of forecasting competition, as well in the recent literature in forecasting. And the bottom line is we just use gradient boosted regression trees, right? And they really perform well in forecasting competitions, the M series. How many of you have heard about it? Not many, that's okay. Basically, it's a really famous yearly competition that is held by this professor from University in Greece. The M stands for the beginning of his name, which I will not attempt to pronounce because I will butcher it inevitably. But what he basically started in the 19 or early 2000s was a competition where basically statistical, old-fashioned ARIMA methods were used. And then come like the M3 or M4 edition, where there were a lot of data into it about retail or in supermarkets and other places. And this is where the first time we had one model basically fit on the whole of the time series, coming on top in terms of performance, really talking in terms about accuracy. But the beauty of global forecasting is that now models, especially gradient boosted trees, but linear regression as well with some clever feature engineering, can achieve a lot in terms of performance and scalability. Not in terms of, not just in terms of how fast that is, but also in terms of how fast the process in of itself is. And so here's just all that it takes to build FunkTime. A powerful query engine to perform blazingly fast feature engineering. I forgot a crab emoji here somehow, followed by just a single method .fit, which is an incredibly familiar API, I would say. But we took it a bit up, and by we, I mean the original creator. Now I'm the lead, basically one of the co-maintainers of the project, and the maintainer moved away. But he really envisioned a much more streamlined API compared to scikit-learn, not to demean it, of course, by any way, shape, or form, where basically we fit the model, and once you fit it, you can just call validate or conformalize and make it generate prediction intervals of your prediction using a conformal prediction, which is another framework I will talk about in PyData London later this year. And the whole point about this is you can use global forecasting models to achieve one of, I wouldn't call it state-of-the-art, but an incredibly good model in terms of performance. But I would argue that what matters about this is that given the plethora of tools we offer to extract features from your data, and the speed that this offers, the real gain lies, once again, in the process. I think I swear this is the last time I'm saying that. And this is basically all the theory behind it, right? I won't go into the details, and now we can do inside the dangerous coding part, which is somehow demoed, because I have a runtime notebook, which is here. But by the way, if you go to the repository, you can also run the code about this presentation and see and run it for yourself, in case you don't trust me. We are... That's open source, right? I mean, that's just total transparency. And while I'll go a bit about depth, basically what we're running here, we're just installing FunkTime, a slightly smaller version than the one currently available on PyPI, because we're preparing for a release in the next couple of weeks, prepare for like 0.10 coming soon, which makes the promises to be stable and depend on a much more recent version of Polars, which means stability, also more compatibility, also much more speed. But just as to make an example, here we're getting some demo data, and this is basically the kind of data you're going to deal with when you work with FunkTime. Time series data, you have a lot of one column that represents the entity, we call it, so the SKU for those in the sector, so basically the identifier of the time series. The second column represents the datetime, and the target column is the price. We just make one assumption right now, is that the data will be in this order, which might be tough. Most of the libraries, including, for example, the ever infamous Prophet, just make the assumption that you have to name columns in a certain way. We just assume about the order, but please feel free to raise an issue if you have something new in mind. Func in FunkTime stays for functional, but I've been thinking about adding a time series dataset class. Maybe that might be a bit conflicting, but that might be one of the solutions for this. But this is how our data looks like. And this is just commodity dataset. So a bunch of observations across time, heterogeneous time zones, heterogeneous time stamps about goods that are traded at a certain price. And you can see that it is kind of unwieldy to get started with, right? Because if you need to perform exploratory data analysis, you need to start getting fancy with for loops maybe and plot a bunch of matplotlib axes all together, and good luck with that. And what we try to do is to simply provide you convenience methods to deal with all of these time series at once. These plot entities tells you how many entities there are across all of your data set. And so you can immediately spot which time series are underrepresented, whereas which ones have allow more complete and homogeneous observation, like a range of observations. But you can also, at a glance, and here it's what I'm saying, I'm using a quite old version because all of this is automated and hidden under the hood of 0.95, but also 0.10. And you can display all of your time series all at once. You can just sample some of those to see at a glance how they behave. And here we see that, for example, the natural gas series in Europe behaves correctly, and then war happens. And tada, here we are with the prices spike. And the same goes for potassium chloride, which I think is used in fertilizers as well. The sunflower oil, because Ukraine was producing, and is one of the biggest producers in the world, etc., etc. And this is hard to deal with, because here this is a really naive data set, but still, it really displays a change point, no air passengers dates, where you will just have a really predictable trend and seasonality. And this is real world data. But what we can do and what we offer, which here is just is written plainly out in code, but from the next release will be just under the hood hidden for you. You can just define a metric. See here, for example, we can just use one of those metrics named coefficient of variation, which is basically the ratio between the standard deviation and the mean, and compute it for every time series. And now we have a way to sort all of our time series and display them by that error metric, or metric that we choose to display them on with. We have a bunch of those. Here I'm just randomly playing out. But still, for example, here they are the series that basically have the ratio of the standard deviation towards the mean that is biggest. And here we see that actually these series that behave well are coal, crude oil, actually the worst, crude, and for example gold, of course we know it, there's been COVID, and then there's been war, so the price has been, the behavior of the market has been crazy, and we try to hedge and invest in securities and refuge goods. And C-phosphate rock, that's another one I was mentioning before. So we have a way to start to, and we want to offer an API that enables the user to glance over a multitude of time series at once, well beyond the just inspect and inspect the residuals or decompose all the time series into trend, seasonality, and residuals. We will start to give an approach to make the exploration scalable. And then here we are with the scikit-learn familiar API to transition from experimentation to, exploration to experimentation. We do have, here is where we try to mix and match a bit of functional programming with the old familiar API. So basically this is, it's basically a decorator, but it's basically a function that returns a function. This is like a curried function, if you want to name it in a fancy way. And there's going to be another incredible talk about functional programming in Python. I think it's tomorrow. Today, in a couple of slots, so make sure to go check that out. And here, basically, we just build a train test splitter, as we were doing in Funtime. And the beauty of this method is that we abstract away the complexity to perform these operations on all of the time series at once. So here, you specify the forecasting horizon, so how many observations you want to keep aside for the final test. And you see here that basically, if you inspect the test set, we did the separation in train and test split all under the hood. So you didn't have to write, for example, a for loop or do the group by of your own. And if you use pandas, they would start to get slow and slow. And then we have and implement a plethora of benchmarking methods. The seasonal naive, for example. We specify a frequency. We say of the forecast, the future forecasting horizon, the frequency of the observation, and the seasonal periodicity. And we can just call method. We define the forecaster. We just call forecaster.fit, forecaster.predict, usual standard sklearn API. But still, you see that the predictions are generated for all the time series at once. So when you do inspect the prediction, you will see them properly arranged according to the time series. And it was computed for every one of those. Here, it's kind of a bit cheating somehow, because, of course, when we do to the modeling part, we just do one model on the whole time series. But prediction needs to be generated for every one of those separately. So we do them for you. And if you look at diagnostics, we just have a plotting method, a plotting submodule with plot forecasts, for example, which we can use to plot a sample of K forecasts, of K series. And here we see our naive method and how it behaves compared to natural gas. Here I'm using, here I'm not using a metric, but we can sort, we can just import from the evaluation module, the rank point forecast function, and use it to sort all of the prediction that we made. Using here, I don't like using mean absolute percentage error. Don't use that in production. Don't use that maybe period, especially if you know that your data is going to get closer and closer to zero, because if being a percentage, being a ratio, it will explode. So don't use this. This is here just for educational purposes. You never know. We can rank the forecast and see which model have the highest and or lowest error. And we can use those to basically display the prediction by the worst, like display the models and see on what series it performed best or worst according to a certain metric. So for example, here we can see that our naive model didn't perform fairly well on potassium chloride, urea, coconut oil, and palm kernel oil, and natural gas as well. Of course, being a seasonal mean, we expect it to underperform when there's a change point, right? Given that also we set like a breakpoint of like a periodicity of 12, which means 1 year on the data that we have. And now we enter with the modeling side, right? And we can always use the good old linear models, because if we pair them with clever feature engineering and we re-implemented the whole of TS-Fresh, which is a famous feature extraction library for time series, re-implemented everything in polars, plus wrote some Rust custom kernels to make it run even faster, you can have like and explore a plethora of feature extraction method to extract signal from your features. And we tried to be a bit more on the experimental side with this and offer like a novel take on the API. So instead of building a pipeline that looks like a scikit-learn pipeline with feature unions, with column transformers, we just accept a list, of an argument parameter. You don't need to write logic to make the shifts. We will do them for you for every series. And basically 2 other arguments that accept a sequence of objects, or just a plain object, of the target transformation, so the transformation that you want to apply to your Y, and then the feature transform, which are the features that you want to extract. So here, for example, I'm fitting a linear model that has basically computes the mean and standard deviation as actually the rolling mean and standard deviation over a window of 6, 12, and 24. So basically, I'm computing a standard mean with a window of 6, of 12, and 24. And then we can use those using all of the methods that polars implements, including, for example, the exponentially weighted average. And this is good. We just called model.fit, model.predict. Here I'm just using a bunch of the dictionary option because you can just call .backtest to perform automatic backtesting. So cross-validation, but for time series forecasting. And we can plot the backtest, and this looks like a bit, I'm just sparkling a bunch of coriander on top, but I swear that if you zoom in, and I think if my browser allows it, then we can see that basically it's just 5 different prediction plotted all alongside one of each other. And of course, we can do all the function and ranking residual, but what I really like about FunkTime, what made me fall in love with it and starting to become a contributor, is the plethora of diagnostics plots that we can have to see at a high level how this performs. And here, I really like this rank residuals combined to plot residual function to display, for example, the residual of the forecaster. And here we see basically how they are stacked together in a distribution to display which time series behaves best or worst in this case. And here, for example, we're looking at the baddies, actually the best ones, and see that we have our estimator is not really normal in the distribution of errors. Some series are more compressed than others, and it really is like really tall in terms of a normal distribution. And this is somewhat okay, and we can kind of do the same with some tree methods and see that you see that the 3,000 year top, like this is a bit more like smaller, so it's a bit fattier on the side. But what we can really do is have a plethora of tools to compare against a bunch of models together in the performance. And this is one of the plots that I really like and I really love to talk about. I don't really remember the name about this, but basically it's just this plot is, it's called a forecast value added. So it tells you the value that a forecaster adds compared to a baseline. So here, for example, we plot the predictions of the light gradient booster, so gradient boosting trees, and then we perform against the benchmark, which are our naive forecast. And on the x-axis, we have the naive forecast, and on the y-axis, we have the light gradient boosted machine. The straight line represents basically the equality. So on the x-axis, you have the error over every time series according to the naive model. And then on the y-axis, you have the error according to the light gradient boosted machine. If the 2 models were the same, we would see them basically aligned along this straight line. And here it's kind of what we see, right? That the benchmark and the forecast error with this map, unfortunately, but still, with a light gradient boosted machine are kind of the same. And so here we can immediately inspect the outliers. So which function behaving oddly or have the highest error compared to a baseline and see if our models are actually more capable than just a baseline. And we can do the same, and we can, of course, compare, and this is extraordinary. If you do just the linear regression against the seasonal naive, we see that the naive model performs really well, because if the points are below the diagonal line, we see that the model below here is better for those time series. So here we overperformed with a naive model. Actually, our linear forecaster underperformed compared to the baseline. And we have another similar one, which basically plots one of the error metrics, the coefficient of variation, for example, on the x-axis against the error of our choice, in this case, the symmetrical mean absolute percentage error, don't use this, for the light GBM boost. And here we see that in this quadrant, we have points where a time series where the error is low and the coefficient of variation is low, good. But here we have a low error in terms of coefficient of variation, low variation, but high error. And so this immediately tells us which time series require more attention. And this is the kind of tools that we would like to offer to make your process of forecasting faster. So the point that I was trying to make was to make the process faster, right? To identify the critical series, provide you a series of tools to just fit one model and see where it doesn't behave really well. Add some more, and then you can customize your feature extraction, which is demonstrated to be empirical, but also in papers and competition, to be the key value to enhance your forecasting models. And so in this way, for example, we would like to offer you tools to see all those time series at once, fit just a naive model, and see where it belongs, and then iteratively see how you can make it work for the whole of your data up to a reasonable level. But here you will see, for example, that liquefied natural gas behaves unwieldily, and then you can customize your feature engineering to, for the purpose to better fit on that data. And I think that basically this is it. Just to give you a vibe about it, of course. And this is a really great feature, and then we have so many more of them. For example, hyperparameter tuning, sensor forecast, and also like a just OpenAI call to analyze the data, whatever. This is just a market at this point. Even terminal applications now have those, and I'm not joking. If you want to read more about it, there are a bunch of references of talks that have been given across the past year. The Discord and Polar's documentation is really welcoming. We try to be too, so please opt in if you really want to. And for that works, I would love to thank you for your attention, and I'm really eager for your feedback about how this project is shaping, about how I gave this talk, so do not hesitate to reach out. I would love to make this project even better and to hear you about how I can make it better and make it custom tailored for your use cases. Thank you very much.
Thank you, Luca. So there is some questions that were in the... There is a slide up for the next.
Hi, it's a fantastic talk, first of all. I have one question about the generalized model, because I would really like to know how the information is shared between the different commodities. When you talk about the linear model, I assume that obviously you scale differently each of the commodities, and also when I think of a linear model, I think that maybe there is a categorical feature that encodes the entity, but this is not sharing information because there is no parameter sharing at that stage, I would say, or really little. So I would really like to know about this. And the other question is, how do you deal with the exogenous variables, if there are any? Would this approach work with exogenous variable also?
So starting from the last question, which is how we do support exogenous features. You can pass them as an argument to the dot fit and dot backtest and whatever methods we do. Going to the first question, yes, basically just one model that is fit on the whole of the thing. Some of the identities, for example, the SKUs or the identity, are treated as categorical features. If you do extraction of features from the date times, for example, you extract the month of the day, the month of the year, it will be treated as I don't remember for sure if it defaults to an one not encoded. It might be treated as an ordinal. That's because maybe linear models in this case don't really perform well, but gradient boosted trees understand those kind of features. You were saying that there might be some not information being shared.
Yeah, how do you have an advantage for having a global model rather than having a single model for each commodity? So how is this information shared?
Since it's just one model, just have one set of parameters. So it knows that they can treat one of the SKUs, for example, as an ordinal feature. So it switches, they're just calling it this way, the bias using that information encoded in the categorical values of the SKU or the entity column.
But do you think that, for example, a linear model would benefit for a global model, or the linear model?
The linear model, maybe not.
Yeah.
That's maybe not maybe likely to underperform, because if you have many features and you fit a linear model, you know that ordinal encoding doesn't really work very well. So if you need to just use one hot encoding, then you will have too many dimensions. It will become sparse. But gradient boosted trees handle this very well.
Okay, thanks.
You're welcome.
Yeah, I will have more questions for later.
Okay. Therefore, the last one.
Thanks for a very beautiful talk. One question: do you know the project SK Time, and do you take inspiration or collaboration with them?
So Christopher, the creator, was once a contributor to SK Time. I was dabbling with it back when I started into forecasting. We didn't talk very much. We should try to cooperate. The point is that we have different goals, and they try to be extremely compatible with the scikit ecosystem and provide anomaly detection and a bunch of other features, while on the other side, we just be more tailored to forecasting with polars especially. So if you just, basically this means if you have a pandas data frame converted to polars, then it works with us. We don't do that for you.
Okay. Thank you, Luca.
Thank you very much. Grazie.
Okay. Test, okay. Yes. Ok.
Pronto, pronto? Funziona? Sì, ok.
Il tuo è da 45 minuti, giusto?
No, sarebbe 30.
30, ok. Ho
Sì,
fatto 11
no, perché era un po' tagliato, sì, boh, insomma,
Vabbè, anche
alla
meglio,
fine
meglio.
farò meno. Tanto alla fine è
Ottimo.
una roba molto
Allora,
leggera.
casomai quando finisce il countdown, ma se non ci arriviamo,
Boh, io credo che saremo. Però nel caso fammi sapere quanto siamo, magari manca 5 proprio per emergenza.
esatto. Ti
Ok.
faccio il 5 dal question
Sì,
time.
ma vedrai che. Grazie. si è incastrato qualcosa?
Sì, stanno facendo un test, ci danno
Ah, ok, ok.
Okay, so now we are in the next speech. Now Fabio Lamanna speaks about sit back, relax, enjoy the talk. A journey to fly radar 24 with Python. I remember there is in the schedule page a link to the slide for the question. So now, thank you, Fabio.
Thank you. Thank you for coming and welcome to PyCon, also this year in Florence. And this talk, yes, is very easy, very relaxing, should be at least, since because I arrived literally 20 minutes ago because of 1 hour train delay. So okay, we are in the themes of the talk. Just a few words about myself. I am a civil transportation engineer. I'm working around transportation planning, urban planning, mobility, etc. And I'm also organizing the Databios Venice with some friends. Tonight we have some Databios here in the PyCon. And I usually do consulting, especially for companies or public administrations in Italy. And today is my third talk at PyCon. 2 years ago, I talked about cars. Last year, I talked about trains mostly, but it was a little bit analysis around GTFS data and some algorithm for clustering data. And the only difference is that once I had a Twitter account, but no more. And there is also only a Mastodon account if you want to follow me. So today we are talking about flights. I think that most of you should already know the Flight Radar 24 platform, maybe some playing or following flights around the world. And today we are talking about the platform and how we can get some data, live data with the Python, and try to reproduce later some outputs that we can get from the website. Flight Radar 24 works tracking with different sources flights around the world, thanks to radar data, satellite data, etc. So you can get the real-time position of the aircraft and all the information about speed, altitude, and so on in real time. Let's talk a little bit about the data. So I have a silver account because you can, of course, get all the information on the website for free with the basic account. You can get several different subscriptions, so the silver, gold, and business. There is an official API, but in beta version of Flight Radar 24. And if you want to get and use data for commercial purposes, you have to buy a business account. So I have, just for fun, for myself, a silver account. So the benefit is that I can download maximum of 10 CSV files of single flight data per day. Otherwise, you can get more data with different subscriptions. you can get also a free business plan subscription if you want to contribute to the tracking of the system. Flight Radar 24 can send you at home a kit to build an antenna, so you can get your own receiver connected to your router and transmit data, and you can get also this business plan subscription for free for 1 year, I think. There are several packages, Python packages, to able to talk with the Flight Radar 24 in a non-official way. And today we are going to talk and use this one, because I tried several, but this one should be the easiest one to get some basic information. This is called Flight Radar 24 API. It's available on GitHub. And of course, you can install it with pip, very simple. So the idea of the talk is to try to do a risky demo on Jupyter Notebook, and to try to get some data and try to reproduce some altitude speed diagrams, some basic maps about some flights around Florence and in general on the website. So I'm going into here. Let's see. Maybe you. Oh no, first of all, this is the website. How many of you already use or known about this website? Okay, great. Perfect. So, so this is the basic map. Maybe less known is the data that you can get. For instance, you can check for a flight, for historical data, and here for each flight you can download here or the KML or CSV file with the basic information about the single aircraft. So let's zoom a little bit. Okay. So the idea is to, first of all, import the Flight Radar 24 API and using some basic packages like matplotlib for plotting data, pandas to get some data frames, and NumPy for little mathematical things, and also GeoPandas for mapping the trajectory of the flight into a basic map. So it should work. Let's hope. Okay. So we are calling the API with this function, and the first basic instructions that you can get is to get basically the list of the airlines in real time. So you can have the name and the code, etc. This is a basic information. Now we can go into more detailed information. For instance, selecting an airline. Okay. So DLH is the code for Lufthansa flights. So we can just call the API, telling the package to get only the flights that belong to Lufthansa. So we are going okay in this way. This is not a big list. Well, it's big, but not so big. But I mean, these are all in real time, all the Lufthansa flights tracked around the world. You can see there are some flights with high altitude, so we might guess that they are still flying. Zero altitude, they might be in the airport, just arrived or on departure. So we can have all the different information about the ground speed. The heading is just direction information and the altitude. So from this, you see that it's basically a list. Okay, so we have each element of a list is a detailed flight. So I'm trying to get the first, for instance. We can get more details. This is a very big dictionary. So we have essentially, I think, everything that we can get from the website directly clicking on the aircraft, even the pictures of the aircraft and everything related to the flight. So basically, we can get navigate into the dictionary. We can get the origin of this flight, which is Osaka in Japan. And this is the code of the departure airport. We can get, let's see, to Munich. Okay, this is the Osaka-Munich flight. Get the Munich code. And these are the information about the travel time. So we can get the departure, scheduled departure, and arrival times, real time, estimated time. So we can get also the potential delays. For those who are not familiar with this is the Unix time code. So we need basically to convert to a more common daytime format. So we can see that this is the departure time. Yes, scheduled departure time so it's tomorrow. So it's consistent because it's departing from Japan. So it should be ready tomorrow. No, sorry, it's today, 23. Okay, so today, tonight, or I don't remember the the time frame, but well, this is already should be already already on air. We can get the trail. So basically, this is, again, a list of dictionaries of different positions along the path of the aircraft. So the coordinates, the altitude, the speed, and this is the time frame of each position. And this is the heading, so basically information about the direction. Let's see how long it is. So we have more than 800 information or points. We can get, or better, we can compose a list of appending a list of latitude and longitude to get information about the track of the flight. This is a little bit a trick because if you plot in a normal axis XY the coordinates, you can get a path, yes, but it's not consistent with the shape of the spherical shape of the Earth. So you can just do some geographical transformation of coordinates to get the correct aspect. So should be okay. So imagine that here we have, no, I don't know, maybe it should be, we'll see. But basically it's going from Japan to Germany. Yes, it might be this one. Okay, well, we'll see later. And now we are using GeoPandas to get the background of the trajectory of the flight. Basically, here with this command, we can get a data set of maps, basic maps of the world. We can just extract some information about the color and the style of the map. And finally, plot the trajectory. So let's see, apart from the, okay, no, it's consistent. So, okay. So it departs from Osaka, and it is already ongoing to the final destination in Munich. Okay. If you are using GeoPandas, GeoPandas is close to release the 1.0 version, so there appear some warnings, but they should be removed later. So just a warning. And finally, we can get from the previous file all the other information about altitude and speed, for instance, and plot this information in real time. So this is the departure and the ongoing information about the current path of the aircraft. So this is nice because you can get also a bound region where you can try to track information about flights. So these are our coordinates, more or less, of the PyCon in Florence. And we can get a radius of 10 kilometers from here and try to capture all the flights that are tracked into in this area. So let's see if there are some flights. Okay, there are three flights, 2 on the ground, I guess, and 1 which is already, well, just departed or is arrival. Let's see on the map, for instance. we are here. So yes, this should be this one, the Vienna to Florence, which I capture here. Should be this one. Let's see, E195 should be the model of the aircraft. Yes, this is this one. Okay. So basically, we are more or less, because this is the airport. We are basically more or less here on the river. So we are tracking a circle of 10 kilometers and try to get all the information within the bound. One last thing you can do is to try to capture more and filter with more than one information. With this call, we can get all the flights belonging to Emirates Airlines, and also the aircraft type, which is the Boeing 777 and another, but should be 777. And also you can get restrict the zone you can where you can get the information in Europe. Get again the bounds and get all the information. Let's see. Okay, these are the a smaller list of aircraft according to this filter. Remember that these information are on real time, yes, but we cannot get historical data with this package, at least if you don't buy, as I said before, if you don't buy a business plan account. In that case, I'm not sure, but you should be able to insert into the library some, I guess, some code, so that Flight Radar 24 can know that you are actually using a business account to get the data. Okay, back to the presentation. I think that's all. I told you that it was very easy, and but I'm here if you have some curiosity or other questions that I might answer to. Thank you.
Thank you, Fabio. If there is some live question, we can choose.
I have one.
Yes, please.
Yeah, with this live data, is it possible to parse this data in a way to determine the short separation incidence between two aircraft? So when at given timestamp, two aircraft are closer than what we consider a safe distance?
I guess so, because I'll get back to the data. Well, you have all this kind of information for each aircraft. So I think that, yes, you can, because you can get all, both the speed, the distance from the coordinates, and also the altitude, because several flights might fly one over the other or on the way around. So yes, I think so. Yeah.
They rather have an API REST, or the library just scrapping the CFV?
I think that it's just scraping the data from the website.
Okay,
yes,
thanks.
Yes. But I guess there should be the link of the package if you want to explore more. This is one. This is it. So it's Flight Radar 24. There is also a Node.js version, but I didn't try it. Very small documentation, but as you see, it's very easy to code with the package, and you can just play and try to get information if you want.
There is another? No? Okay. Okay, so thank you, Fabio.
Thank you.
For this,
Thank you.
Ti aiuto?
Grazie. Adesso ho finito anche troppo presto.
Va bene.
Un, deux, trois.
Okay. So now we are in the last session of this morning. And now Miroslav Shedivi talks us about how solving two-word problems in computer science using pandas. Thank you, Miro.
Ciao a tutti, sono molto felice di vedere tanti Pythonisti qui. In realtà originalmente ho voluto fare questo intervento in italiano, ma poi mi sono reso conto che italiano, sebbene è una lingua che sia utilizzata molto in Europa in cucina, ad esempio in tedesco, ceco, slovacco, non diciamo pasta lunga, pasta quadrata, pasta in forma organica o ornamentale, diciamo lasagne, spaghetti, no, non diciamo spaghetti, diciamo spaghetti. In tedesco, ceco, slovacco si dice spaghetti. Quindi in italiano è una lingua utilizzata molto in cucina o arte, ma in computazione c'è un'altra lingua che è più dominata, and that's the reason why I'm going to switch to English. If we stay in Italy, you have the huge mountains, Alps, but we are now here in Italy, we are at the south of Alps. But do you know which is the mountain of Alps that is most to the north and to the east? And that is over 2,000 meters. That's right, that's Schneeberg. What you see here, this is the view from somewhere between Bratislava and Vienna to the west. And the white mountain that you see, that is Schneeberg. And the stuff that is in front of that, these are some wind turbines. There are hundreds of them. And a wind turbine, this is something that not only generates energy, it also generates data. A lot of data. It is like an organism. It tells you, oh, I'm too hot, it is too cold here, I have too much energy, there are too many birds flying around. And even imagine that a wind turbine, of course, it turns like this, it gets the wind, but it has a sensor that if the wind doesn't come from here, but it comes from here, it turns around. And then the wind comes from there, it turns around again. And then it turns around with the wind, but at some point, well, I don't have the right microphone to show it to you, but imagine that I have a microphone with a cable. I would have a problem with the cable. Because the wind turbine, if it turns too much to the right or to the left, then the cables, they have some length that are allowed to turn several times. But after 3 times, the wind turbine will tell, wait, there is wind, but wait, now I have to turn around back 3 times in order not to break my cables. And even there is one turbine that you can go there and visit. You can just climb the stairs, and you are not on the top of it. To get to the top, this is not so easy for mortal humans. But there is, if you see on the shadow, there is a small ring below where you can just walk up stairs and then see how this works. But now back to the data. Let's say that the wind turbine sends me CSV files. I will show you one CSV file. This is how such a CSV file looks like. It's long, very long, and it's narrow. So if we zoom into it, you will see that there are actually 3 relevant columns. There is something like a timestamp. The second column is actually the data, exactly the parameter that it consists of the device and of the parameter or of the physical entity. And the last one is the value. But now here you see that the problem is that if you want to put this, for example, into pandas or into database, the first column, okay, that's timestamp. The second one is some string. And the third one, is it float? But sometimes you have data that comes as an integer. Sometimes they should come as a Boolean. But if you put all of these into one single table, then the third column will be a float, and if it tells you, for example, that here is an amount of 3 of something, then the float can be shown as 2.99999 something at the end, because that's how float works. So this is for the wind. What in my job, I don't only work with wind data, I also work with PV plants. And PV plant, if we are playing with languages, there is anyone speaks some Chinese here? there is the Chinese word yang, and the sign, it looks like an animal with horns. And this word yang, it means at the same time, it means a goat and a sheep. There is if you want to be very specific in Chinese, you have to use a mountain goat or a shanyang, that is goat, and a mianyang, that is sheep. But, well, if some languages don't distinguish between the two, the people who own or who maintain PV plants, they know very well what is the difference between a goat and a sheep. Sheep, peaceful, very happy. There is grass, it can eat it, and it stays below the PV panels. But the goat likes to jump and destroy them. PV plant also sends us a lot of data, and if we visualize a CSV file, it can look like this. And if I told you that wind turbine was more like an animal that has some feelings and some states, then a PV plant is more like a plant. So something that is like a mass, that is a structure, but it's a mass. It doesn't have some central brain. And when we look more specifically at this data, at the files, you will see that there is some date and time zone, depends on where you get this data from. But then all the parameters that come from it are in columns. And now imagine a PV plant, if it is twice as large, then it will have twice as many components. There are different components, transformers, inverters, plenty of sensors that do a lot of stuff. But all of them are somehow numbered. And then if you have, for example, a thermometer somewhere, then all over you will have 20 thermometers, and all of them will give you some temperature of the panels, of below the panels, of the ambient temperature, and so on. And all of them will appear as extra columns. So you will have a very wide table. In this case, I can tell you we have some Austrian PV plants that give us CSV files with 8,000, 10,000 columns. There are people who want to open this in Excel. Even if you put this into database with 10,000 columns, good luck writing SQL on that. So we have seen the two extrema. And, well, there are now two hard problems in computer sciences. Who knows it? It's the cache invalidation. The problem with cache invalidation, well, for my talk, I had to adapt this a little bit. I was searching where I could find this cache invalidation in this. Imagine that if you have one long table that always when something gives you some information, you just put it there, then it's easy, because if something doesn't give you information, then you just don't put it into the CSV file, and it's okay. But if you have this wide table, then every time you will have, every second, every minute, you will have to give this 10,000 columns, so 10,000 values. And if there is something that doesn't give you the information, you will have to decide, do I put null? Do I put something else? Do I repeat the value that was there before? And then you will have to interpret it. So usually we are talking about 3 dimensions. You have timestamp. Timestamp is something that increases every second, every minute. And you have device and parameter. And we have seen that there was the idea of the device and the parameter. So parameter is something like temperature, power output, wind speed, wind direction, and so on. They were concatenated into a single field. But it makes sense actually to divide it into more fields, because if you have something that measures the wind, speed, and direction, then you can have 100 of them, and all of them give you 2 parameters. All of them give you 2 wind direction and then wind speed. So if we look at this, what we received from the wind turbine, you see that in the second column, the cells, you have this concatenated, this device and parameter, which is possible, but you lose the information about, well, I have 100 devices that measure the wind speed and wind direction. I would like to have this normalized a little bit. If we now take this other extreme with the 8,000 columns, of course, you have a problem. If you enlarge your power plant and you add a few more devices, then you will have to change the structure of your database, rewrite or SQL. You don't want to do it. But I was searching, well, what would be the best compromise? And this is what I found, actually. I go and group the data according to the type of the device. The first table on the left, this is the anemometer that measures something with wind. And there are always 2 columns. I have the timestamp and the device, and then the two physical columns, and I know that wind speed, it is always float, and wind direction, let's say, it's always integer. You don't need float for that. And for temperature, you have always only one column. So you will always have 2 plus 1 or more columns that will give you the complete information about the type of the device. As I said, with the 3-dimension time step is something that will increase every second. Device is something that can change because you can add new devices or remove the devices, pause the devices, and then they will just not appear there. But every anemometer always gives you these 2 physical values. Every thermometer gives you 1 value, and there are devices that give you more values. So this is also nice that solves actually the problem with cache invalidation, because every sensor that is there that gives you the information, if it is not there, it doesn't give you the information, and then you don't have holes that you have to solve what I'm going to write there. The second problem in computer science is naming things. So this is nice. We have something in English. That's why I told you that, well, Italian with all the accents, this is something that is maybe something that you would like to use English or language that doesn't use all the accents for naming such things. Don't forget, names of people cannot be invalid. So if someone's last name is Shedivi, then write it as Shedivi, not as Sedivi. And then we have some other values that, or some other parameters that come from the input. So we have ambient temperature, and you see this is already a little bit not so ASCII. Well, you have spaces, you have square brackets, but you have already these circles for degrees, and you can have longer names, you can have different ways of writing, describing some parameters, and even you will have something that is maybe in a different language. And this is something that finally we can get use of a nice animal that will help us to solve this, and that's Python. In Python, a variable name must be something that is a string, that is not also a string, that is an identifier. But if you say that something is an identifier, which means that it can be used as a variable name in Python, which means that there are no spaces, there is only letters or letters, digits and underscore, and it doesn't start with a digit, then you are on the safe side, because if it works for Python, then it works for Databricks, it works for databases, for PostgreSQL. You can name files according to that. You are on the safe side. If it is ASCII, well, for physical parameters, you usually don't need something beyond ASCII, except for angstrom, but we don't use angstrom here. And is lowercase, well, this solves the issue with uppercase L, O, and 0, and so on, so they look quite well. But what can we do with this subset of data, of columns? We would like to normalize them somehow. Anyone knows the program called GraphViz? This is very useful if you have any problem with plenty of data and you would like to find the dependencies or visualize and find the dependencies or relations between data. GraphViz is a language that, well, is a text language. You write this file, you pass it via GraphViz, and it will give you SVG, PDF, or some graphic that you can visualize. And if I give it here, so it means that I divide or split every word by underscore, and then split it, and then look what are the dependencies, then I will immediately get this. And you will see that there are some things that repeat. That, for example, temperature of the main oil tank in Celsius, supplementary, and so on. So you see that there are arrows, and if you want to find a nice system of naming stuff, then find a nice hierarchy. So I will now jump to the result, where I looked at every single thing and tried to make the naming of the things as short as possible, and this is what was my result. You see that at every word, at the very end, there is the unit. Just before it, there is the noun that describes what it is about, and then you have something that is more or more specific, so less general. And you see the main supplementary oil tank temperature in degrees Celsius. So you try in your system, in your knowledge base, to find the smallest graph that covers all variable names that you have. And in the result, you actually want to have as few connections in this visualization as possible. Because it's perfect if after temperature there is always degrees Celsius. If you have some manufacturer that gives you the temperature in Fahrenheit or in Kelvin, then, and your internal standard is in Celsius, then you want to convert it. When you import a variable that says external temperature in Fahrenheit, then you want to name it external temperature degrees Celsius, and when importing you want to calculate the difference. And that's it. So this is graphics. I think this is very useful also if just not connecting to the topic, but if you have some project and you want to find the dependencies, all you do is in the language on the top you define the tasks, and immediately you visualize how the results looks like, and you see, oh, there are things that should be connected and they are not. You just add it to the source code, reprocess it, and the result will show you immediately where the connections are. So we were now with the two hard problems in computer science. Is there any more problem that you are aware of? Yes, it is off by 1 error. If we look at the data that comes from some energy meter, for example, and you get this, okay, this is in Spanish, but the first column is the timestamp, and then the second column, IV, this is actually how one Spanish manufacturer distinguishes between daylight saving time and standard time. I means invierno, so in winter, but we are now in summer, so actually when I created these slides, I made an error. And the last one is some variable, not important. But now, tell me, what is the best way to aggregate these numbers by day? In Pandas or in some other language, in SQL and so, you would maybe just take the first column, you would extract the date out of it and group by and make the sum. But the problem is with the line, with the two middle lines, for example, the line with the 23rd of May 0000. What is it? It is the 15 minutes of before midnight, or is it 15 minutes after midnight? If you usually in measurements you measure something and then at the end of the 15 minutes you look at the sum and you write it down. So actually this represents the 15 minutes before midnight, and you shouldn't aggregate it to the next day, you should aggregate it to the day before. So this is something that you have to distinguish between two types of values. And I found this graph that, well, a random graph that represents the temperature and precipitation. Everything that represents a state, so a temperature, wind speed, a speed of a car, is something that is instantaneous, usually. And if I am missing a value, I can usually interpolate between the value before that, after that, usually it will be more or less okay. But you cannot have the yearly temperature. There is no sum of yearly temperature. There can be maximum, minimum, or average. But for the precipitation, this is exactly the amount of some material or something that has been created, energy, during a time. So for our timestamps here, I would like to define somehow that the 15 minutes are not starting or ending somewhere. That are the 15 minutes that are defined in my timeline. How do I do that? In Pandas, everyone who works with Pandas knows that there is this timestamp. But who of you has ever worked with period, with a type of period? And this is exactly the time-related unit or object that allows you to work with something that has a period that starts somewhere and ends somewhere, and that is regular. So for example, if I do PD period now D, I define a variable that is a day, length of day, that is defined for today. If I can even ask for the start time and end time, and it will give me the first millisecond, nanosecond probably, and the last, no, microsecond, nanosecond. The first nanosecond and the last nanosecond of this. But the period itself, it is something that will cover the whole day. And also I can do simple mathematics with it, because I have the period representing today, and I can do -1 + 1, and I'm adding whole days. I am not this -1. I don't have to define, take a timestamp and add 1 day, subtract 1 day. It is I'm adding or removing or subtracting integers that represent these periods. I have periods of more of any length. So for example, if I do y, so it's a year, it gives me the current year. And you see the second parameter of the result is a y minus December, which is a concept of a year ending in December. If you have some financial years that start, for example, in April or in October, then you can define it as a year that ends in March, that ends in September, and then it will calculate with them, and it will cover them, and you can do all the calculations with that. There are also quartals. So quartal standard is a Q minus dec. It means that the year ends in December. So my quartals are defined by 3 months of the year, but you can also move that around. For months, okay, that's, well, months. Then there is, you see this week. This is also possibility to define weeks that end on Sunday or on Saturday. Days, we saw them already, and hours and minutes and seconds, and also something in between. There is, however, something that I would like. When I discovered this, I was very happy. I refactored my code, and it worked. It was much more compact and self-explaining. But I had an issue. For some reason, I needed to divide a day into blocks of 8 hours, so into 3 blocks. Now, if I say I want the current hour, now we are after 12 o'clock, okay, it gives me this. This is the hour of between 12 and 13. If I tell it, give me a block of 8 hours, I would like from midnight to 8, 8 to 16, 16 to midnight, but it actually looked at where I am now, and it told me, well, the block is starting now. So it's from 12 to 20. If I do -1, it moves from 4 to 12. And this is not what I wanted. I wanted to divide a day by 8 days, by 6 hours, 8 hours, 12 hours. I wanted to do it now in 8 hours. So the shortest piece of code that I found was this. I even wrote a suggestion last year, maybe, to GitHub to find some way of describing it shorter, because here I have to put these 8 hours twice in my code. But there was, until now, no reply. Maybe I should program it myself. That's how open source works. The periods, using periods in your code is something that helps you to tell every method what to use and what you expect back. So for example, if you want a method to read some data from somewhere and normalize it into periods, then I would suggest to create a period range. So actually something like datetime index, but with period, well, a period index, and define it explicitly what you want in that, and then pass it to the function. And then the function should return a data frame, and actually the data frame should have the index that is exactly the same that you ask it for. And with this, you can very easily ask, for example, for the 3 days until yesterday, so the 3 periods of daily periods that are until yesterday, or for example, year to date, which means that all daily periods from the beginning of the year until yesterday. And that's it. Keep your data frames in good shape. Thank you very much.
Thank you. So, yeah, I finished it before, so good lunch.
Enjoy your lunch.
Thank you.
Grazie. Oops.
Okay. Okay.
We also go to Italy.
Yes. We are in the.
We in their fast.
because I just fixed them all.
Okay, we check if the. Okay.
Sure.
Yes.
Oop, that's not full screen.
Yes, yes.
Test. Okay,
Yes.
cool. Sweet.
Okay. I give you after I can down.
Okay.
There are 2 minutes. Okay. 2 minutes at the end. After the game over, we have 5 minutes for the answer question. If you go to after the game over, you have minus time for the question, but you can
Okay.
continue.
Is there, I don't have the questions up here on the slide. Okay, yeah,
yes.
perfect. Sweet.
And then, so, when the start they show, when the talk starts. And I have to reload and it starts. Yes, yes. Okay, so we can start after the lunch break. So now Tim Payne talk us about high-performance data visualization for the web. Thank you, Tim.
Cool, thank you. Thanks, everybody, for coming to this talk. My name's Tim. I work at a company called Cubist Systematic Strategies. which is the like quantitative systematic trading arm of Point72, which is a hedge fund. And I also teach in the computer science department at Columbia in New York. Full disclosure, this is the link to the slides. I like pip installed one thing like 30 minutes ago, and everything broke. But I think I got it all working again in the 5 minutes at the front. So if something doesn't work randomly, just be prepared for it. But I'm sure everyone's been in that same place where one dependency changes and the whole world crashes. So this is a talk about high performance programming for the web. I'm going to try and minimize the amount of JavaScript because nobody likes JavaScript. And try and address some background, some motivation, why we made this library, but also what it's good at. Talk a little bit about the library itself, which is called Perspective. I'll do some live coding and some demos, and hopefully everything goes well. So the background here is, we're all Pythonistas. We have access to a huge number of web frameworks. I listed a very small subset of them here. And obviously, whether or not you're in Python or using JavaScript, for example, you have a ton of data visualization components. But despite all of this abundance, and I'm not trying to speak ill of any libraries, some stuff is still pretty clunky, pretty difficult to do, even with some more complicated, some more advanced of these libraries or components. Some of these pain points are going to be virtualization. So this is my home Airflow setup, which does some stuff. And I hate seeing pages like this, right? So pagination. We're always prone to paginate things. Sometimes that makes a lot of sense, but other times I just want to scroll through the whole grid. I just want infinite scroll. I want the table to be virtualized behind the UI so that, I don't want my UI to be loading gigs and gigs of data, but I would like it so that as I scroll, for example, my UI is being smart enough to proactively grab just what's visible on the screen. So a lot of frameworks just can't or won't support unbounded data sizes. So fetching a range of things, a lot of times they just don't support that. Another pain point is dumb grids. So most grids that we use, like tables that we visualize, are dumb. At the best, they might support filtering and sorting. So I might want to say filter this column by some value or sort by this column. Maybe they support Spark charts. So those are little inline charts that you can have in the middle of your table. And maybe, which is a big maybe, they support pivoting. So there are a lot of really great grids out there these days. I went to a talk on great tables recently, which was fantastic. So definitely check that out if you haven't looked at it yet. This is an example of a relatively advanced grid. This is AG grid. So you can see even here, I obviously picked one of their examples from their page. Even here, this is pivoting by country and then sub-pivoting by something. I don't really know. It's kind of hidden here. We see it's a pretty sparse grid. We see a lot of visual space is taken up by configuration of things. If this is kind of the advanced grids, you can imagine that this is pretty difficult to configure and still doesn't work that well. And even if you get this is just the grid form, right? What if I want to see the same data pivoted in another form, a heat map or something like that? So this is the other thing that you see a lot of, which is visual overload of just let me present as much data as I possibly can on one page. Usually there's not a ton of meaningful data. This is a classic one like Grafana. And oftentimes we do this because the components that we're using don't let us explore them further. So I present you the grid. It has been pre-configured by me, the developer. You, the end user, might not be able to do anything with it. So again, maybe you can sort a column or something like that. You definitely almost always can't switch between visualizations and stuff like that. And the pain point number 3 is streaming. So all of these different things, the frameworks we talked about, these pain points that I previously mentioned, they all exist for static data, but they also exist for streaming data. So if you're paginating things, how are you going to do with streaming, right? Are you going to do some amount of polling for updates and then repaginate things? It's pretty prone to race conditions. And a lot of visualization frameworks also just don't really make this easy. They expect you to have all your data up front, and if you want new data, you have to re-render them or recall them. So I put an example here of the Fast API WebSocket example server where they've got some front-end code. It's kind of a lot. And then here's the back-end code, which is also kind of a lot. I love Fast API. My example here is going to use Fast API. But the takeaway here is just that even with what is probably the best web framework we have right now in Python, doing stuff with streaming data is still kind of complicated, still pretty difficult. Oops, not yet. Cool. And then once you're talking about streaming, and we talked about pivoting and aggregations and stuff like that, what if you have end users, right? Now you have a engine that has to provide streaming updates and potentially have streaming aggregations where each one of your users is maybe grouping by different things. Each one of your users is applying different filters. It obviously can get pretty complicated pretty quickly. And same deal, like a new user joins. What view of the world do they see? Do they get a snapshot of state? And then you provide them incremental updates. Again, for most frameworks and UI tools, like you have to do all this work. You have to provide that snapshot, know that they're a new user, et cetera, et cetera. So we wrote this library, me and several other people, called Perspective. It's on GitHub. It looks like this, Perspective. We wrote it at a bank for bank use cases. And the kind of tagline is interactive analytics and data visualization component, which is especially well suited for large and or streaming data sets. Now, it's not tailor-made for like big data or anything like that, but it is very good for small to medium-sized data sets that might stream. They can be static as well. And the key thing there is that interactivity of it, right? So everything that I show you, I'll try and show you 4 different views of the same data. And that interactivity is all going to be powered by Perspective. So homepage, this is all linked from the slides, but this is basically the GitHub page. There's a link to the homepage here. You can find lots of examples, which I'm going to go through in just a second. So concretely, what this means is that Perspective itself is a streaming pivoting data engine. So you load data into it. You can think of it kind of like a database, but it's not really a database. It's written in C++. It's bound to Python on the back end. So we just have like PyBind bindings. And on the front end, it's bound into JavaScript via WebAssembly. So we compile the same C++ code in the back end and for the front end. And it has the same version of both. And then there are UI plugins. So it's a data component. But when we want to manifest that data with different visualizations, there are plugins which are written in a combination of Rust and TypeScript. And I'll show you a bunch of the different UI plugins in a second. So one of the cool things is that like the backend and the front end are both the same code. So it lets you kind of have different architectures. You can use it just in a JavaScript kind of fully client-side way. You can have a Python web server with a JavaScript-based views. So the symmetric C++ engine basically means that when we're transferring data back and forth, we basically don't need the GIL for stuff because we don't really need to prep stuff on the back end. We can kind of send it as is the front end, and it's the same code running on the front end. The virtualization, so that was that wanting to have kind of unbounded grids. We send diffs back and forth via Apache Arrow. So we try and keep it as fast and get that data back and forth as quickly as we possibly can. So I'm not going to talk too much about the pure client architecture. It's quite cool. You can have just a web component, a one-liner in your HTML, and maybe one line of JavaScript. And you have this full component without any Python and potentially without any web server if you're just pulling static data. But I'm going to talk about the kind of client server having a little front end. It'll be a tiny amount of JavaScript, so nobody leave quite yet. And a little bit of Python code. And those front end, as I said, they're web components, which basically means they're custom HTML elements. So there's a perspective-viewer that you can use. The plugins provided are the table. Obviously, I'm going to talk a lot about grids. But a pretty powerful grid engine, but also charts, heat maps, bar charts, line charts, scatter plots, stuff like that. And maps come out of the box. You can also kind of write your own plugins. So if there's your own way you want to visualize things, it's a pretty extensible system. And one of the key elements here is that we kind of give the power back to the end user to explore their own data. So I'll show you the configuration of how do I want to pivot things. You can pre-configure it so that it loads up by some default. But as an end user, you can also interact with the UI to make new pivots or do sorting or even derived expressions and stuff like that, user-derived functions, whatever you want to call them. OK, so at this point, everyone stop believing me maybe. But I'll show some code. And it's available at this link as well. OK, so I'm going to start with some standalone examples from the website, just to kind of motivate further what can be done. Then I'll look at the Python side in a notebook. We have a Jupyter widget, which I'm going to use an old school Jupyter notebook because I just broke my Jupyter lab, as I said. And then I'll show taking that notebook and turning it into a web app. And hopefully, it's going to be a small enough amount of code that everyone follows along and could reproduce it. If not, the code is posted on that link, so you can look at it there. Cool. So here we have a bunch of different examples, trying to do different things, show different types of data. Here's an example with just some like Olympics medals. So this is perspective running on the back end. It's doing some pivoting by sport, some splitting by age to produce this kind of aggregated view. And then the plugin that I'm using is the heat map plugin. So we can see group by age, split by sport. I said it backwards. There's a little bit of layout stuff here as well. So I can, for example, close this. And I think there's a second one there too. So same type of data, but organized in a different way, group by sport, order by name. And so all these interactions are purely happening on the front end. There's no user code that we need to worry about for these things. You can change these plugins. So I can turn this into a data grid. Oh, I disconnected it slightly, didn't I? Yep, there we go. So here's that same stuff as a grid. This is not a huge data set, so it's not a ton of data. But we see that same type of thing. We get some of these niceties that other grids have. So for example, I could do something like some spark bars, right? People like to see visually kind of these differences. Some other cool things you can do is, because you have this kind of symmetric engine running everywhere, you can do things like cross-filtering. So I can say, if I have a collection of these tables, let's just keep the same one, but we'll show it in two different forms for now. Let's turn this into a grid. That's not a very interesting grid. Let's get rid of those group bys and split bys and just make it a flat grid. Oops, nope, no expression columns yet. No. All right, let's just throw all these other ones in. There is a whole expression engine, but that's going to be the subject of a later talk. Cool. So I can do things like cross-filtering, which is basically where you apply these same operations, in this case, like a filter operation, across all of your views. All right, so when I click on boxing, for example, it'll just cross-filter all the other perspective viewers on the page by that filter, right? It would be like where sport equals boxing, something like that. So it's we tried to adopt a little bit of like a SQL-esque kind of syntax. I'll show some other examples. So this is just to get a sense of like what it looks like and the types of things you can build. Here's that maps viewer. I live in New York, so got to have a little bit of a New York shout out. But this is a visualization of the City Bike, which is like our bike rental service that we have. So hopefully it will load. You can see this is kind of like scatter overlaid on a map engine. Same deal here. And again, all that same cross-filtering could apply. So if we did like a pivot, this data set doesn't really have a good pivot, but we could kind of sub-filter down all the other views. One more, we got some themes. This is some movie like revenue data set. But same deal, you've got your cross-filtering here. So you can cross-filter by studio. This is kind of a heat map, I think, of the whatever it is. Oh, this has some expressions in it, which is kind of cool. So these are like user-defined functions. They're defined using a library called exprtk. And here we're just bucketing IMDb ratings and bucketing Rotten Tomatoes ratings and looking at a kind of heat map of those two. So lots of different things that you can do, lots of different visualizations that you can build. And all these things that I'm kind of doing here, you kind of allow your users to use as well. If they keep this little thing closed, they never have to edit anything, you can get rid of it. But if you want, you kind of provide your users this ability to have kind of a Tableau-esque experience. And it takes a little bit to understand some of these, how these things work, but it results in a very powerful kind of end user experience for data interactivity. Okay, so I'm going to do a demo now, some Python stuff. I'm going to use two libraries. One is called Superstore. I just needed a data generator library, so I wrote a little one. Also, Pandas deprecated the time series generation. So this just is going to generate some data for me. In particular, I made it generate some data about machines. So it's going to create a bunch of machines, give those machines a bunch of utilization, give them some role, some number of CPU cores, whatever. And then it'll randomly generate jobs that are running on those machines. And I'm also going to use a library called CSP, which is a Python stream processing library, which basically makes it very easy to think about data streams. It's a forward propagating graph that you can have things ticking and kind of pushing data around. These two are not terribly important for this talk, but that's just where the data is coming from. And again, this notebook and all the content here is available on the GitHub repo. So I'm just going to import perspective. We have a thing called perspective widget. I'm going to use that library to make some machines, that Superstore library. So again, just kind of randomly generated ID, cores, region, zone, whatever. I wanted to have some nice things to pivot by. I can randomly generate, for example, some usage information. I can randomly generate like the status of that machine. It's got this much CPU use, this much memory free, whatever. And I can randomly generate some jobs, though I don't know, it depends on the machine what type of jobs it will create, so that might not return data right now. This little block of code, again, not particularly important that you know what it does, but basically I'm going to create 4 of these perspective widgets, and I'm going to use that CSP library to just generate data and push it into them. Right? Again, stream processing in Python can be a little tricky. CSP makes it easy. I'm basically just saying calculate some machine usage, and then push all the machines into one of those widgets, push all that usage information into one of those widgets, push all that status information, et cetera. So not a ton of code, not particularly important. And then I instantiate my perspective widgets. I'm going to do some sorting pre-configured on the Python side. I'm going to have the settings be false, so they won't have those configuration views available. Create those things. They are somewhat statically typed. You can feed data into them, and they will try and expand, but your columns need to have one data type, similar to most data frame libraries. I'll do a tiny bit of layout using IPyWidgets. I'm just going to make a 2x2 grid of these things. So we can see, looks something like this in my notebook. I have to keep the font size pretty big, but you can see I've got 2 and 2. And then I'll just run CSP, and we'll get some data feeding into them. We'll see some stuff is updating here in real time. Right? This is the machine utilization is updating every second or something like that. Right, we're generating some jobs randomly. All right, and these widgets are nice. Those same interactions that we can do on the front end. So, things like, changing a group by changing sorts, you're also able to do on the back end. So in this case, this is the status widget. And these things are going to oscillate between active and idle and stuff like that, kind of at random, based on what's running on them. So I'm just going to reconfigure them to be, in this case, a bar chart. I'm going to group by status. So I should basically see a bar chart of how many of my machines are active, how many are idle. And I'll change the columns a little bit, add some aggregations. All right, so now I've done that here, and a little bit easier to see things updating in real time. See the jobs, I think they update every 5 seconds or something like that. All right, so the takeaway from this is, if you're in a notebook to start, if you're never building a full-fledged web application, there's still a lot of good usage here. You don't need to be constantly typing in pandas or polars expressions to pivot things. You can kind of load it up and then interactively do things, and it is a widget, so it is reflective, right? So if you make changes via the widget, you can kind of interrogate the Python object and see what's happening there. But this is a talk about web applications, so we should probably talk about a web server. And it's basically the same code. So I have a little bit of code here to make a perspective app. To hook perspective into a web server, you basically need something to run perspective, right? Run the perspective manager. We have examples on the website. There's a link here. But they're also available from the perspective homepage. For Starlet, so Fast API, Starlet, that kind of ecosystem, Tornado, and AIO HTTP maybe. But the code isn't particularly interesting. It's basically something to bridge that gap between your web server's WebSocket and perspective, which wants to communicate across it. So basically instantiating one of these perspective Starlet handlers and plugging it into my app. And then I have a little bit of code here to just serve my index.html and the JavaScript assets. And then I put cores because I never know how to use cores, so I just threw it in there just in case if something wouldn't break. I've got the same code from my notebook. So again, using the CSP library, just making some of these ticking data streams and then plugging them into perspective, right? I have them ticking 1, 5, and 5 kind of second intervals. And then this kind of plugs it all together. I host these tables. When I host a table on the web server, it'll be available from the front end. The front end itself is also super easy. I know I told you I wouldn't show you too much JavaScript, and it won't be too much JavaScript. But basically, I have these perspective viewer web components. I gave them some IDs so it would be easier to track them. And then I kind of connect to my web server, and I just load up the web server connection. So it's 1, 2, maybe 3 lines of substantive code. And then same deal, I can pre-configure some of that visual, the plugin that I want to use. In this case, I want that status to look like my my Jupyter notebook. I want it to be a bar chart. I want to have some aggregation, whatever. So I can run this. And it was broken earlier, but hopefully it'll work this time. And I can pop over here, and it should start ticking in real time. There we go. All right, so again, I have all that same interactivity here. I can reconfigure things. I did say high performance, though. So 5 seconds and 1 second isn't really high performance. So let's go and make that 0.1, 0.5, and 0.5. And let's run it again. Now it should look a little nicer. That's pretty good. But, you know, it's a demo, so let's make it 0.01, 0.05, and 0.05. And that should be really good. All right. And I should mention that there are other ways we can look at this data. So same thing is running. Here I just have a slightly more complicated view that I produced, where I'm going to have some, if I don't destroy my machine first, where I have some more. It's the same web server running both of these. But here I have some additional aggregations being done. I have a 3-layer group by kind, region, and zone. I have some Spark bars here happening in real time. This is my vanity page, right? No one's actually going to look at this. You can kind of get a sense for where these incremental changes that we made using Apache Arrow for diffs, being able to configure these things where it starts to pay off when you really scale up. All right. My computer's going to run out of battery, so let's hop back. So takeaways, basically, if you need to build kind of relatively high performance, obviously nobody's going to look at something that's ticking that quickly. You want to have some interactivity. You want to have this ability for end users to reconfigure things. You want to have streaming data. You want to pivot. You want to provide kind of different views on the data. Perspective is a great choice. It's Apache 2 licensed, open source. Lots of examples, though never enough documentation. And provides a Python widget in a notebook and a relatively easy to use kind of Python library that embeds with basically any of the popular web servers. Yeah, I think that's it.
Thank you, Tim. So there is no questions in Slido. There is a question live.
I did put my questions on Slido, but anyway, I'm going to read them. First question is, can the user configuration, basically the configuration that the user does in the browser, be saved to the server side?
Yeah,
for example,
so
in the user profile?
The configuration and the data here is separated. So all of the configuration is done via JSONs, basically. So it has this kind of save restore. I've typed it so many times, it's already there. Kind of save restore interface. I know this font is super small for people to read. It basically says, plugin data grid, plugin config. So all JSON based, so you can easily reload it, save it. As far as saving it to the server, it doesn't come out of the box, but it's basically just a JSON. So one of the first things that I write whenever I write a perspective app is I have a little drop down of basically do you want to save your layout? If you do, in the JavaScript, it's just save. That gives you back a promise to a JSON, and then you can store that. A lot of times I just store it in browser storage. There is a new version which has this client-server interface written in Rust, which is going to do some more of that, some more configurability from the Python side of the front-end component. But right now, the kind of client-server interface is almost exclusively data.
Okay, and second question was, how easy is it to integrate the front end with let's say, another existing framework in React or Vue.js that you...
Yeah, so that's the nice part about just having it be a web component. It's just a perspective viewer element. So once you've imported the library, you have a custom element that you can do whatever you want with, so it'll work with React or anything like that. You have to worry about sometimes React lifetime, so you want to give it a ref and make sure that you're not regenerating the web component excessively, but otherwise, I use it all the time from React.
Thank you.
Thank you for the talk. I would like to ask you about what are the limits that you have. You say that in terms of big data, it's actually get to medium-sized big data. Is it? I saw that there are used extensively by Arrow. So is it something actually that allowed using a connection to Spark data frames or data in partitioned parquet style column and dataset.
So there are two parts to this. I think if you have a flat grid, you can put as much data as you want in that. The interface is purely virtualized, so as you scroll, it will just load up the next chunk of data. Once you start to do aggregations, it slows down as it would naturally, because if you have to do a column sum in a massive data set, you have to iterate through the data set. One of the nice things there is some subset of the aggregations can be done online. So once you've done a pivot, if you stream in additional data, a subset of the aggregations don't need to recalculate the whole column. They can just pull in the new data. The current version, the client-server interface is pretty internal to the library. So you could have just the JavaScript component and interact with whatever you want on the back end. That would work totally fine. But some aspect of that pagination, not pagination really, but it's kind of like pagination under the hood, you would have to implement yourself. In the next version, which there's a PR open for it, we make it a little bit easier for you to write your own client or server or whatever. So you can basically not have the perspective engine be used for the data storage. You could connect it to DuckDB or any other database or backend storage system. So it's basically exposing that interface as an end user implementable thing. Today though, data limitation wise, it tends to be several gigs that some of those aggregations start to break down. I still think it's beneficial to do. There's a number of things you can do as far as limiting the total size to make things quick, especially for streaming data. But if you have a massive data set and you just want to visualize that data set, I think there are probably better tools.
Okay, I have the question on Slido now. So, can you customize the tooltip of the graph?
The tooltip of the graph, I'm not sure if you can. That's a good question. You can choose which fields go in the tooltip, I think. But so it'll show the 3 pivots and then whatever you put into this tooltip. But I don't think you can customize it further other than by, for example, doing a computed column. Right? So if you do a computed column, I can say I'll probably type in something nonsense, but I could do CPU +1 or something like that. All right, now I have a derived column, which I could also put in that tooltip. So you can kind of see new column 1, and it was doing something dumb. It's just doing CPU +1. But outside of that, you can't configure too much about how the tooltip looks internally. That's not a us thing, really. That's these plugins use other libraries. So this uses, what is it, D3, FC-D3, something like that. Uses a D3 kind of finance-oriented chart library. The grid is a separate grid plugin. The maps is one of the maps libraries. But if you did want something fully bespoke, you can always implement your own plugin.
Okay. And the last question. Can you point the backend to a Parquet file or a PyArrow dataset with multiple Parquet files and explore that data in the UI?
Yeah, so we have one example on here. I think it only does CSV. Oh, no, it says CSV or Arrow. That's good. Should review my own examples beforehand. And then I wrote a little wrapper as well, which I'm definitely not going to be able to find right now. It's called Perspective Parquet, Perspective-Parquet. It's on PyPy. If you go to that library, I don't remember exactly what it does, but I think what I did was I wrote a little plugin for Jupyter to just let you point at a Parquet file or something like that. But I think basically serving a Parquet file is as easy as read the Parquet file and call perspective whatever table dot update with the data.
Okay. Thank you, Tim.
Yep.
Yeah.
Okay, is the microphone is open?
Mhm.
Oh, it's perfect.
I have.
We can meet in mute. Okay, good.
Yes.
Okay, so we can start with another session. Now, Mia Balic, he talk about combining Django RAM and the Fast API in a single app. Thank you, Mia.
Hello, everyone. I'm Mia Baic. Today, I'm here to tell you an intriguing story about combining two very different frameworks together. I'll share my personal insights on how to navigate through it, highlighting the advantages, struggles, and lessons learned along the way. Now, let me share with you my experience with Python frameworks. The first framework I had an experience working with was Flask. I use it for my hobby projects and for my diploma thesis. What I like about Flask is that it's a very lightweight and very simple framework, and it's also very easy to use. Then I began working in a company that used Django. We were creating typical CRUD apps, and Django was great for the apps we were creating. Everything worked out of the box. Django ecosystem was great with lots of libraries, and in general, we didn't have to tweak things a lot. Everything just worked. And finally, I joined my current company, Atacama, where we use Fast API, but with one exception I will talk a bit about later. These three frameworks are currently the most used one in Python ecosystem. According to a JetBrains survey from 2023, Django leads the pack used by 40% of responders, followed close by Flask with 38%, and Fast API with 25%. However, the most interesting fact about Fast API is its rapid growth and its huge adoption, rising from 14% in 2021 to 25% in 2023. And now, I'm curious about your experiences with frameworks. How many of you have experience with Django? Raise hand. Okay, so around 90% of people, so almost everyone. And how many of you have experience with Fast API? Okay, around 50%. And now comes the fun part. How many of you have experience using both Django and Fast API in a single app? Oh, yes? No? No. Okay. So no one. And indeed, if you have a look at the most popular fast API open source projects on GitHub, you will notice that none of them use Django ORM. Most of these, in fact, use SQL Alchemy. And now you might be wondering why. Why is Django and its ORM so popular, yet it's never used with fast API? To find out, let's dig deeper into each of these frameworks. Fast API is a newer framework released in December 2018. It's very modern and very flexible. It's built on the shoulders of two giants, Pydantic and Starlet. Pydantic is a Python package used for data validation, serialization, and documentation. Starlet is a lightweight asynchronous framework or toolkit used for building web services. That means basically that any of its components can be used independently. Its main features include things like WebSocket support, session and cookie management, test client, core, JZip compression, static files, streaming responses, background tasks, and many, many more. As you can notice on the diagram, Starlet uses UVcorn and implements SGSpec. The most notable feature, or the feature for which Fast API is best known or the most used, is its performance. Fast API is one of the fastest Python frameworks, and its exceptional performance is largely due to its asynchronous capabilities. Django, on the other hand, is a framework with its first release in 2025 and has been the most popular Python framework for years. It is a batteries included framework, meaning it comes with a comprehensive set of features right out of the box. Additionally, Django is quite opinionated. It was designed to promote specific patterns and specific approaches to web development. When it comes to its ORM, it's primarily synchronous. Asynchronous features have started to be added from version 4.2, which was released in April 2023. However, full implementation of asynchronous features is still ongoing. Now, the question is, what are the benefits of using Django ORM with Fast API? So the situation where basically you have Fast API, so why would you use Django ORM with it? From my personal experience, Django ORM is very easy to learn. I switched to Django ORM after using SQL Alchemy, and I find it easier to learn. And also, it's mostly because there are fewer things one needs to take care of. For example, session management. You need to take care of it by yourself in SQL Alchemy. I also have experience with Alembic and Django migrations, and I find Django migrations easier to learn and easier to manage. Also, Django has a very rich ecosystem with lots of tools you can use. If you type Django on PyPy, you're able to find over 10,000 packages containing the word Django in them. If you head over to djangopackages.org, you can find lots of different projects to explore. Fast API is a relatively new framework, therefore its ecosystem is smaller. One of the killer features of Django is its admin panel. It is a panel where you can add, delete, or update data belonging to any module. It's a friendly user graphical interface, which is great because it can be used also by users who are not programmers. Fast API doesn't have any built-in panel, so if you want to have one, you have to use third-party packages. Django is also well-maintained and supported by a large community. This community not only contributes to the framework's development, but also organizes events like DjangoCon, where developers can gather together. DjangoCon also includes sprints, where everyone has an opportunity to contribute to Django or one of its libraries. I personally have been to the sprints, and for me, it was a great opportunity to poke around the code base and to learn more about how Django works under the hood. Django also has great documentation. You can find lots of resources and support online. There are forums, tutorials, Discord groups, and even podcasts all about Django. If you want to check it out on your own and connect with the community, head over to djangoproject.com/community. This is where this screenshot is from. And this is one of the things I personally am missing a lot with Fast API. It's a new framework, so its community is very small. Now, if we take it from the other side and ask ourselves, what does Fast API bring to the table, and why should we use Fast API instead of Django? The biggest reason you would probably want to use it is its improved performance thanks to its asynchronous capabilities. Fast API also includes a powerful feature that automatically generates documentation for your API endpoints. This interactive documentation is provided in the Open API format, and it simplifies your initial setup. So if you open your app and navigate to /docs, you can explore and interact with your API. Alternatively, if you prefer a different style, you can use /redoc to view the documentation in redoc format. And it also utilizes the Open API specification. And this feature is not built in Django. Fast API utilizes a nice feature called dependency injection, which really helps to keep your code clean and testable. In order to see how it works, let's see an example. Let's say we have a service that fetches data from an external production API. We have a route that utilizes this service. Each time the endpoint fetch data is called, and an external call is made. Now, how can we test this in an easy way without actually calling the external API? Here is an example of what our test might look like. First, we create an async mock object that has some return value. And if we want to swap our dependency and use the async mock object instead of our production service, we can call dependency overrides. Then we proceed to ask our endpoint as usual. So in just one line, we managed to swap our service with another. I think this is a very nice pattern which improves testability and helps you a lot to keep your tests clean. I've not seen this pattern being commonly used with Django. The last feature I want to highlight is Fast API simplicity. Sometimes working with Django feels like there's a lots of magic happening behind the scenes. This might be helpful when you're trying to set up something. However, it can also mean that everything is fine and everything works until it suddenly doesn't. And then what? Then you start debugging. However, with Django, to me personally, sometimes it's very hard to figure out what's happening under the hood. With Fast API, it has a very straightforward approach, and it makes it easier for you to understand how is your application put together and how it works. And I think this can be a great advantage when troubleshooting. Now, I told you lots of benefits from using these two frameworks together. But there is a reason why this combination is not commonly used. Let's explore some of the unique challenges it presents. The first thing you notice once you're starting working with a code base that mixes asynchronous and synchronous code is how often this exception occurs. And it occurs in places you didn't even know existed in your code base. How many of you working with Django have ever encountered this exception? 1 person, 2, 3, 4, 5 people. So not so many. If you decide to use both, then you're almost guaranteed to run into it sooner or later. One of the big reasons why I believe this setup is not commonly used is because managing synchronous and asynchronous code adds another layer of complexity you have to take care of. Let me share a quick story called There and Back Again. When I joined our team a year and a half ago, our code base was sync first. That meant all of our methods were synchronous, and when we needed something asynchronous, like for example API routes in Fast API, we use our asynchronous, we just use sync to async decorators. I witnessed a situation where my colleague was working on rewriting the entire code base to an async first approach. Back then, Django had released support for async or M, and the idea was that now, when we can have everything async, why not try it out and have the whole code base async instead of having it half sync and half async? The change initially seemed successful. Everything worked. However, the devil is in the details. While Django has added lots of async features, there were many features it still didn't support, like async transaction, for example. So everything had to be reverted back to sync first. One of the great features of Django that I already mentioned is its very rich ecosystem. However, these tools don't work with Fast API. There are cases where these tools don't work at all. So for example, I tried to use PyTest Django XDist, and it did not work because Fast API uses Starlet's test client. And there are cases where these tools work, but they have to be tweaked a lot. So they don't work out of the box as they work with Django. When you encounter a problem, what's the first thing you typically do? You Google it. However, with this setup, you will find that there are not many examples on the internet. So you're left on your own, and basically, you just have to experiment. And the last point I would like to touch on is the initial setup. With Django, you can simply use commands like start project, and you're ready to begin. Similarly, with Fast API, a few lines of code are enough to get things moving. However, with any custom setup, such as this one, where you're combining unusual elements, it will inevitably take more time to get everything up and running. Now, let's explore how this setup might be implemented. First, let's have a look at the diagram. We have a Fast API application that uses Django or M for database communication. Where do we start? We are integrating two different frameworks, so we must configure them separately. We begin with Django and its database layer. First, we modify the settings.py file used by Django. I've only changed the database name. Everything else remains unchanged. Next, we need the wizgy.py file to import the Django settings module and launch the application. Now, let's turn to our main.py file where we consolidate everything. Here, we set up the Django settings module, call Django setup, and populate the apps with our installed apps. Now, Django is ready. The second part involves setting up Fast API. We start with creating a Fast API instance, then we define our routes and connect them. For deployment, I prefer using Docker. The Docker file specifies our base image and working directory. We copy our requirements, install them, then copy all necessary files, and export port 8000. Finally, we launch the app using UVcorn, specifying our main file, host, and port, and our app is ready. So if we open now localhost and type in /docs, we can see it works. Moving on. How do we create an endpoint that lists some data stored in a database? Let's see an example. First, we define our endpoint path, add some description, and a response model using Pydantic. Then, we make a database call, which is wrapped in the sync to async decorator. It's a coroutine, so we must await it. And the fetch data is then serialized as a Pydantic module. For Django versions above 4.2, you can use aget directly without the decorator. The implementation manages synchronous and asynchronous code under the hood, so you don't have to take care of it. However, keep in mind that while Django has added lots of async features, it's an ongoing process and not everything has been implemented yet. When you call the endpoint, you can see there's some data return. Now, let's move on to tests. The principle here is the same as for setting up our main app. First, we need to set up Django. We do this by defining where our Django settings module is, populating apps, and finally running migrations before each session. Because we want the database to be clean for each test run, we need to create a fixture which truncates all tables after each run. Then we move on the second part of our setup, which is the Fast API side. We create a fixture where we basically import the app as is. And the last part involves setting up a client to which we pass our imported app and configure its base URL. Now, when the setup is ready, let's look how we can create a test that evaluates the creation of a module. First, let's look at a unit test. We will write a test which will assess a service method that adds a new book, and it does it without a database. For that, we will use a fake repository which might look something like this. So basically, instead of persisting data into a database, we store it in an array which we can access later. We start with creating a request with some data. Then we call our book service, but instead of using its normal repository, we use a fake one. Then we call the method and pass the request data, and after that, we can access the array where the data is stored. Finally, we can assert whether the stored data equals the data from the request. If you would like to write an integration test to test your entire endpoint and to use a database, you could write it like this. First, we create our test that uses a database fixture that takes care of truncating tables, sets up the book app, and includes a client fixture. It also uses the fixture books, which creates some books just to have some data to test on. We call the endpoint /books and assert that the response code is 200. We can also define the expected data and then compare the expected data with the received data. And that's how you could set up a test. So we've seen how it might be implemented, but you're probably wondering about the right structure. If you start up with Django, you'll find that the structure is already set up for you. That's because Django likes to guide developers with certain best practices, including a predefined structure. FastAPI, on the other hand, is super flexible and doesn't really point you in any specific direction regarding how to structure your project. When it comes to bigger projects, I personally lean towards a module-based approach. It's predictable and extensible. It's used in, for example, Netflix project Dispatch, which is one of the biggest open-source FastAPI projects I've stumbled upon on GitHub. And this kind of structure is also mentioned in the FastAPI best practices repo, which I'll link to a bit later. And this structure works pretty well even if you use Django or M. All right, so we have discussed the benefits of its setup and the challenges. I can show you how it could be done, but the question remains, should it be done? I personally love working with both frameworks. However, if I were to start a new project from scratch, I would probably check out Django Ninja as it gives you the best of both worlds. Alternatively, I would either go full Django or FastAPI with SQL Alchemy, depending on your project requirements. It might happen, though, that you find yourself working on a project that has already integrated two different frameworks together, like me. Or you're maybe migrating from Django to FastAPI, beginning with the API layer. In these situations, I encourage you to experiment with mixing technologies. It's great fun because you have to tweak things a lot and you learn a lot about it during the process. And I'm very interested about your experiences. Have you tried combining different frameworks? How was it for you? Did it work? I'll be here around till the end of the conference, so please come and talk to me. And at the end, to quote my esteemed colleague who joined our team and expressed this during our first retrospective meeting. It's crazy, but it works. I'm Mia Bajc. Thank you for your attention.
Thank you. There are no slides, but there are in the live. Any questions? Or it's okay?
Nice talk, well done. One question about the history of the project. Do you know why the decision was made to use FastAPI? Because something like Django REST framework is pretty helpful as well and has automated documentation and things like that. And it looks like a lot of the benefits of Fast API you had to almost turn off. Yeah, that's basically my question.
Yes. So the app that we are developing basically is a data visualization app which works with real-time data. And the biggest requirement is performance. It really needs to be fast because it works with real-time data. And the reason why to use Fast API is because it's one of the fastest Python frameworks, therefore it makes sense. Now, the question maybe is more like the opposite. If you already use Fast API, why do you use Django or M and not, for example, SQL Alchemy, which is commonly used? The reason why to use Django or M, as far as I know, in our project was because there was a requirement to have admin panel, because lots of our users are not programmers, but they often have to debug something, for example, consultants. And for them, Django admin is a great tool because you can just go there and to check out what is in the database. You can interact with your models without having to connect to the database and to manage the infrastructure stuff. So the reason why to do it was because of the panel, admin panel, basically. Thank you for your question. It's a great question.
Okay. So in the last... Yeah. Sorry?
Hi, I have a question. Is the example of that setup available anywhere on GitHub?
Yes. So here, the first QR code is go to my slides. And if you open that QR code, basically it will lead you to my GitHub page, and there you have slides, and next to it there is a setup which you can check out.
Thank you. Thank you, Mia.
Thank you.
sì, sì, no, no, sì. Okay, so we are now starting the next session. Now Yash Sabo talks how to code more, draw less, and debug just a little. Thank you, Yash.
Hello, hello. Glad to be here. Glad to have you all here. This is my first time in Florence, or Italy in general. And I mean, there's so many galleries, so many drawings, and I'm here talking about drawing less. So, all right, so let's start with what the agenda is. So today I'm going to talk about a tool which I built for my team, my department, my company, which helps in visualizing the architecture diagram and also helps in debugging if you have any errors. And that automatically refreshes as soon as you make any changes in your architecture or anything in your system. So today we'll be talking about what was the motivation behind building this tool, the approach that we took as a team to build this tool, and how you can do it if you want to do it for your organization, and the walkthrough also, like how you can do it in different steps, and why this tool will be beneficial for you and your organization. And in the end, I'll take a few questions. All right, so a little bit about me. I'm a software engineer at Bloomberg. I work specifically in New York office in the dividend forecasting team. I can talk about like anything related to my team later on if you want, if you have any questions. And before that, I was doing research work and studies between distributed systems and machine learning. Right now, mostly I do finance and application building. All right, so regarding the tool. So what was the motivation? So what happened was last year, especially in COVID, the business grew crazy, and we started hiring a bunch of people. Specifically in my team or in my department, we hired literally like 30 plus people. And because of that, we started onboarding new people and mentoring. So when I started mentoring the new joinees, the newcomers, what I found was that there was a gap. The gap was between, like, we had a lot of, let's say, knowledge, like, hey, this is the software, this is the documentation, this is the tutorials, these are all the things that we have for you to learn about. And it was like pretty sufficient if you take everything together. But then there was a problem. And the problem was that everything was just everywhere. And what I mean by that is that there were multiple diagrams, there was a lot of documentation out there, but let's say they were all distributed. Some were in form of, let's say, wiki page, some were on a GitHub page. Everything was just like not organized, and which is something which I've seen in my previous companies and previous wherever I've done internships and work and everything. I was like, this is a common theme. On top of that, I think within my team, we had a bunch of, I would say, the same software or same application or same system, we just had multiple views of the same thing. And which kind of makes sense because some were technical and were for engineers, but some were for, let's say, just manager. They don't care about like which service is calling which service. All they care about is, hey, which product, like, what is the main gist of it? And that is justified, but that is a problem. You have to, if you make any change to anything, you have to update everything out there, which is just like not scalable and not the best way. So, and on top of that, as I said, there was no single point of access too. I had to literally, like, I'm not kidding, I had to give more than 25 links. I like, hey, these are 25 links, go do your homework and come back to me if you have any questions. And I don't think that is the right way or right to approach the problem. And on top of that, once we figured out this was a problem and I started talking to, I would say, the managers, the team leads and everything about it, they were like, yeah, this is something which we also see when we are debugging. Let's say when we have any client issues and considering it's a financial product, we have to act within few minutes. And in that case, we have to debug, like, okay, let's say the service is crashing or something. Like, yeah, we are not able to pinpoint quickly, but we may be able to do it within time, but we want to be quicker. How can we do that? So targeting both of them, we thought, hey, can we come up with some solution? So let's identify what the general problem is. In documentation or anything when it comes to visualizing how the system looks like, we like monolithic versus distributed architecture. And on top of that, you don't want to be reminded that, hey, like whatever you've done is out of date when, especially when you need it. You want to know before that. So what an ideal solution would look like. So it should be single source of truth that, hey, I just give you one link, I give you one page, or one place where everything is there. It's not distributed, it is very easy to access, and everything is condensed in one place. On top of that, if anything changes in your system, it can be auto-generated, auto-synced, and auto-refresh. How can we do that? Like, I don't want to be reminded later on that, oh, we did this addition, some engineer made these changes, but we have not reflected this in any of the things. So when, let's say, there is an error, and you're trying to figure out, oh, I didn't know we were dependent on this package, or we were dependent on this databases in some or the other way. And second, I think this is my personal, like when I was bringing, I was like, especially even while I was studying, like why are we drawing still flow charts? Why are these like boxes which are tagged as, oh, this box is a database, this database is talking to this Kafka topic or something? Why can't it be just more immersive? Like we are here hiring UI UX designers out there and everything, and like why can't we make the experience for us as user, as an engineer, just more aversive, more dynamic in nature, and let the diagram speak its mind. So our approach, before we go into the whole stepwise, like let's understand what basic architecture diagram is, or how can you visualize. It's very simple in its form. It's pretty much what components you have and what is the relationship between each component. On top of that, the best relationship that is being done is human. So why don't we add human into the mix? We'll see how we do that. And we'll use, now considering if you've seen the pattern, the components and the relationship between, like if anybody knows what a graph database is, it fits into the problem solution. And we'll use Python for it because, hey, it's a great language and that's why we are here. So little bit intro on people who've just worked with SQL and not worked with graph databases before. So Neo4j, that is just one of the graph database type. Like there are multiple graph databases out there and you can use any of them to solve this problem. It's just we use Neo4j and it just works great. So in short, what graph databases is nothing but node and the relationship between two nodes. All right, so this is me. I have a manager, let's say Dwark, I report, and that is the relationship. I have a colleague in the same team, Kang, and I work with him. It's as simple as that, nothing crazy, okay? Now, how would you define this when it comes to code base? It's very simple. This looks like a big code, but it's pretty much just the definition and the documentation. But it is just one liner to create a node. It is as simple as write a create keyword, use it, name the type of the node. So let's say in the previous case, it was this node is type of people, okay? So let's say we'll call that node type equals to people, and the name of the node would be Yash. And that's it, you're done, you create a node that way. The next step is creating a relationship between two nodes. All you need is the name of the node 1, you need the name of the node 2, and what is the type of the relation? It could be work, it could be managing, anything. And on top of that, you can add a lot of metadata. And what that means is, let's say, when did I create this node? And is this node still active? This is just an example. We'll see that this metadata is what will help us in debugging later, because you'll add so much like properties to each node that will help you figure out what is the architecture, how it looks like, how everything connects, and how we are storing everything in one place. All right, so now that we understood that, okay, graph databases and Python, that makes sense into this whole problem solution, and this metadata logic, once you add that into it, it becomes a one-stop document shop. All right, so I'm gonna give you a UI sneak peek. So like, you can use any UI, you can convert this, you can hook this graph database into like a web API, like you can use, there are a lot of plugins out there in React.js. If you wanna use, you can make Like what you see this, you can make this like a space theme if you want, but there are multiple ways you can visualize this, but I'm just going to use the in-house Neo4j, which the UI that they give. Very simple to understand, nothing crazy. Just to go over what it means is, we are going to use the query, the power of query in this databases to help us overcome the different views that I was talking about. Based on what query you write, you can actually see, let's say, a 10,000 feet overview or a very detailed diagram that you want. And that can help you figure out, hey, this service is talking to another service and how everything is related to each other. So in general, what this query, let's just talk about this query, right? Match, and let's say this is a component. So all our repositories, like those would be called components. Here, the tool, what we are using is called interactive. We are making a tool, like we've named it interactive, and the name of that is interactive. So it's as simple as give me a component which is named as interactive, and it will show me this, and on top of that, it will show me everything, or all the other nodes which have relationship to this center of attraction, I guess. So in general, what are the steps, right? Step one is spot it. It pretty much is any data out there in the wild that can help you figure out what your system looks like. That is as simple as that. Then you scrape it, you collect it, do whatever you want, just get that data, merge it with your all the other data which is there, then graph it. Like you have to write just those two little steps which I showed the code base, just like graph it up, put it into your Neo4j or any graph databases you're using, and then repeat that for all the data sources which is present out there. Now, I'm going to let's start with a very simple data, right, which is common to everyone pretty much out there, GitHub, all right? So in this, everything that you see on GitHub or anywhere in general, that is a data for you. That will help you enrich your debugging tool or your architecture diagram. So let's say for simplicity, we have created this, and it says that, hey, this, whatever is in the README, that is your description of your repository or of your component. And we are going to store that as one of the properties. You can also use things like, hey, when was it last accessed? So let's say here in the screenshot, it shows 2 minutes ago. So you take that, you get that data. There, like here it shows, hey, Kangmin Bay actually edited this. You can actually also get that. So everything that you see here can be scraped and can be used, because that will help you figure out, hey, okay, who made this change? What was it? Who's the point of contact? Everything is relevant, especially when you're on a time crunch trying to figure out, hey, how this system works. So now that you figured out, let's say this is the this was the repository, interactive, and if you see, we've added some of the properties. You can add more properties. We've added a bunch of properties, but these are something which we are showing here. One is like, what is the last access date? Was it active? One, yes. What is the code source? So like if you see, like this all is actually clickable. Like on the UI, when you go, like once I give you this UI, you have a way to navigate to all the repositories and you have all the links out there. If you have a video tutorial, you can add that into, let's say, your README, and you can create a parser for it. That's what we've done. And if an organization is linked to your repository, you can also have that and like put it in there and say, hey, which team owns this repository? So let's say there's a huge problem at like a parent level, and you see all the dependencies, and you're like, all right, which are the teams I need to notify right now that, hey, things are going wrong, and you see what is your impact. Now you do this for all the components out there, and you make a little graph, okay? It's as simple as writing one query, match, n equals to component, and give me all the components out there. Now, you've figured out all the components, all the services, all the databases, all the Kafka topics, so everything out there, you have it in your system. But now you want to figure out which component is calling which component storing in which databases, and everything. A good example of that, we have distributed trace, and I'm sure like a lot of organizations out there also do. That is one way to figure out like which service is calling which service or which databases are being interacted. And you can use that to figure out, okay, these are the things which are happening. And this is one of the screenshots, like, hey, I'm hitting one Redis server, or which, like, you can figure pretty much everything out in distributed trace. And the ones you cannot figure out, what you can do is you can create a file on your root repository, and the tool itself will go and figure out, hey, what are the relations, and I can put that in. This is useful. Like, you might think this is a very simple thing, and like, what is the significance? The significance is pretty huge, because I'll talk about it later also, but the idea is you're isolating the responsibility just to the owner of that code base. Now, why is that important? There are, let's say, you work in a team or in a department where there are like 60 people, there are like more than 100 code bases. You don't know what is going on in each code base. All you know is the code bases which you worked on or what you've been trained on. So, and if you're trying to create, let's say, some holistic view out of it, and you're like, all right, who is talking exactly, and is this even correct? So you can write this in this file maybe, and like tell, okay, for sure, these are the proper relation, and these are the proper invocations that are happening. And what is happening with this is you are getting the actual truth, and you're isolating the responsibility. You're only responsible for your code base. And what happens with this is if everybody in the team is following and is doing it diligently, then at all the times, your tool will always be updated, and it will be refreshed every time you update the file. Now, on top of that, package dependencies. This is a huge use case in our, at least in my team it was, because let's say there is some security issue that was found in some external package that we were dependent on, or the version that we were using. We were like, all right, this is supposed to be not used. All the repositories which are out there, this has a security issue, like just remove it, use some alternative. This has to act immediately. And you have to, like, there is a time limit when you have to do it. And during these times, the first course of action is which are the services or which are the core repositories which are being impacted by this. And once you add this again in your tool, like the tool will take care, it's very easy to figure out with one simple query that, hey, which are all the services which needs to be checked, and you can keep a continuous track of it. Now, we've got the nodes, we've got the relationships, and this is how it looks like. So it starts with, let's say, interactive. It says that, hey, it is being invoked, like it talks to Kafka, like let's say Kafka topic, which is relations, one is of node. Then it talks to the Neo4j database. The Neo4j databases is actually also being talked via graph service, and you get like pretty much the entire relation, how everything looks like. Okay, honestly, you just need to create few scripts, and a very simplistic view can be very easily developed. But the idea is that the way you get data, the parsing, that would take time as you enrich your tool much more later on. Now, let's say the next part is adding the people. So again, I'm just giving an example that is GitHub. You can figure out like, hey, who are the contributors? But that does not mean that they are the only contributors. Let's say your team lead did not directly contributed, but he's also, let's say, responsible for it. So maybe you have an organization database out there which just stores, hey, how does your organization look like? Or who, like, let's say, even if, let's say, some repository is tagged with some organization, what is the, which people consist of them? And you can take all of that and you can make a team. This is a very simplistic view. Let's say this is Bloomberg. This is being managed by Haim. And then these are two teams which are managed by my manager, and I'm part of one of the teams, which is Index. Now, once you have this, now you just need to join this with the previous graph. And how will it look like? So this is a very simplistic view because we are talking just one repository. We are talking just two members of one team. But it is like when it comes to, like when I did just for my own department, it was like more than, I don't know, 10,000 nodes out there. So like once you do all of this, this will help you. And here also, you can figure out like, okay, you only want to see 25 nodes, you just put a limit, and this is how it looks like. Just to go over, this is interactive. Again, you see that, okay, I own this, I'm part of Index, this, and like you can see, and then later on, if I want to, let's say I'm on vacation or I'm right now here at conference and something goes wrong with this tool, who do you contact? Okay, you see that, okay, there's another person out there who's available. And why this is important is specifically because when somebody new comes in, specifically, like they're like, who should I talk to? Like I'm starting to work on this tool. Who is my point of contact? Yes, you can ask me, but when, let's say, something is owned by someone else, you don't know who's the proper point of contact. So all of this combines into this one graph. And remember, all of these nodes have their own metadata, have their own information out there. Now, let's talk about the views, which helps you figure out what are the different perspectives. So let's say you want to figure out all the services which are present. So since we had added the metadata, which is like, what is the type of this node? Is it a service? Is it a database? What is it? So you can just like add, hey, give me all the services which are present. Second is you want to find out all the deprecated services. So since we added access date, you can figure out, hey, whatever was not touched more than a year ago, you can just write that query out there and figure out, hey, these are the things which we are not maintaining or maybe not, like it is not relevant, we should take a check. And okay, this one is, which is highly used from our space, is that, okay, let's say the component is JSON load. I want to figure out all the databases, all the downstream databases it is hitting directly or indirectly. So it is, once you figure out what is the graph query language, it is pretty easy. All you're trying to figure out is find me all the neighbors where the type is equal to databases and is connected to JSON load component in some or the other way. And once you do that, and you just get this graph, it shows that, okay, it talks to Splunk database, it talks to Neo4j database. Now, all of this, why is this beneficial for you? So first is zoom in, zoom out. Pretty much the idea is since all your data, everything is stored in one place and you can use the query, you can make multiple different queries out there and make different views. And if you're deploying this on your website, you can have different query for each page and have the same system and a different way to visualize that. And everything comes into one place. If you want to show the metadata where it is there, you can also just show it. Also, if you're being very playful with it, if it has some, let's say, video tutorial or whatever, as soon as you hover, it can start playing video and everything. So it's you can create a very fancy tool if you want. Meanwhile, you can also keep it very simple if you don't want too much knickknacks. Second is static versus dynamic. The idea is everything happens automatically. Every time you make a change in the repository, in the system, anywhere, it automatically refreshes. And it is a great user experience because it is also isolating the responsibility. You're only responsible for your own code base. And which is very helpful, specifically when there are different departments within the same company. Because there are so many things going around, and you're like, okay, I'm talking to this service. I don't necessarily own the service. There's completely different team which owns this. I don't understand. For me, I'm considering them as black box, and I don't have enough bandwidth to create an architecture diagram for them. So what happens is they create their own, we create our own, everything gets merged into one, and it's amazing. And that also helps later on when you're trying to combine different data from different departments. And you already know that, hey, these are how the components are talking to each other. These are the data that is getting impacted. And that helps a lot in trying to figure out, how's your department doing, how's your company doing, and how the entire system architecture looks like. So just to give an example, so I work specifically in dividend forecasting team, which is we predict what the next dividend would be. So let's say, I don't know, IBM pays dividend next quarter or whatever. And so there's a lot of data that goes into and a lot of data that goes out. We want to figure out hey, what is that data incoming? What is the data that we are impacting? If anything from that top level does it impact any of the forecast? Does it impact any of our clients? What are the clients that will be impacted if our forecast does not go through correctly? So this all is pretty important when it comes to this tool would be very important just to try to figure out like what is the whole data flow from start till the end. And that is pretty much it. So any questions?
Thank you. Okay. Thank you. I check if there is some slide any questions of you are okay. Meanwhile, I check.
Thank you. I've got two questions. I ask them at once. Question number one is, have you invented everything on your own, or have you seen some talks or read a book or article about it? And question number two, I missed a step. So you kind of have several components, and how can you guarantee that every component gets into this one single graph? Are they all GitHub repositories, or does every repository need a certain file? Or how do you guarantee that every part of your architecture is included in this diagram?
Yeah. So the first one, yeah, there was no proper inspiration. Like we definitely like researched into like, is there a good way we could represent the architecture diagram in some way or build a debugging tool? We did not, I built everything on my own, and I did not, I would say, directly took inspiration. I definitely like researched, is there out of the box something present, but nothing like fit into the box for us specifically based on the data that we were dealing with and everything. So to answer your question, first one, yes, it was built by me and a few other engineers in my team. And yeah, for the second one, it will take into consideration all of them. You can do it two ways. One is either you make sure that all the scraping that is happening, that is consistent. See, you do your testing. And when you do testing on a small scale, you do check, is everything happening for those small, let's say, a bunch, like for your department. If it works great for your department, it will work for a bunch of departments. So we did a testing, and we made sure for different, I would say, let's say, different repositories of different kinds, is it working correctly? And it was working correctly. And if it was not, we were enhancing things and everything. Is the parsing okay? Everything we did, and it works great for us. Also, we also have a bunch of other, metadata in our company, which makes also sense for us that it is easy for us to keep a track because we are already having a database saying that, hey, these are the components which are already there. So we took, I did a check that, okay, these are all the databases, let's say, my team owns. Is that being shown on the graph? So everything was matching, and everything worked as expected.
Okay, yeah. I read the question on Slido. So it's possible to show how looks like the code for automatic graph creation?
No, we cannot show the code. No, we cannot show the code. It's proprietary.
Okay. And what existing tools, such as RDoc, did you consider before undertaking this effort?
Can you repeat that?
What existing tools, such as RDoc, did you consider before undertaking this effort?
So we started the research 2 years ago on this. Like that was when we started looking at this problem. And at that point, we did not find any solution which catered towards us. Not that I remember, things might have changed, I don't know. But there might be, but nothing stood out to us which solved the problem.
Okay, thank you. The last question. The last question.
Hi, great talk, thanks. Yeah. And so I have a question regarding more of a process level question. That is, how do you organize a team or a very large team in maintaining this kind of scheme? Because I think you expect every developer working on some specific project to add information inside this graph, because yes, it's automatic, but the nodes you need to add it yourself. So how did you handle this part like at the process level?
Yeah.
Let's see.
So at the process level, it was very simple. It was literally you just, okay, everything is automated. So when I say automated, other than this file, nothing has to be maintained by any developer. And what that means is that all you need, there are scrapers out there. There are different data sources, let's say distributed trace, that it has a lot of things that it is stored on our databases and everything. Or if you use distributed trace from like third party, they can also give you the information, like which service is calling which service. Once you have all of that information, that is all automatic. So all you need to do is either run a daily job, or you run a trigger, or you can hook it up as, let's say, as a listener. So all of those things can be easily hooked, and only thing that you want to maintain, let's say for some repositories which are using some coding languages or something that is not being tracked by distributed trace, all you need is this particular file in the root of your repository. That's what we did. That, hey, what are the, for this part, so this is, let's say, this is PyCon, this is the repository name. What are the relations? So it is talking to this database, it is talking to this service. And since this particular repository is being owned by me, I know as a developer who I'm talking to. As soon as I add another dependency, I just update this, like this particular file, and all you need to do is ask everybody in your department. So for me, let's say it is 60 people, everybody is given a tutorial like, hey, this is a new tool, we are going to use this for debugging, please update this whenever you make any changes to your repository. So once you do that, it is just isolating the responsibility. And on top of that, like if, let's say for some languages, you anyways need to, let's say you have a Docker, and in Docker, let's say you tell the type, it is a database, it is you're using some other different type, and once you create a parser also, if you create a smart parser, you can also identify a lot of things from the Docker setup also, that hey, these are the services I'm hitting, or these are the other things which I'm, what do you say, responsible for.
Thank you.